Hello there and welcome to Life Beyond Seen, where curiosity slows down, thoughts soften, and science is allowed to wander without urgency. This is a place for listening rather than rushing, for wondering rather than arriving. Tonight, we're not chasing answers, we're letting them drift past us gently, the way bubbles rise when you stop trying to hold your breath. Our journey this time leads downward, not forward, not outward, but straight down, through miles of water, through pressure and darkness toward a place most maps politely ignore. The Mariana Trench is often described as the deepest point on Earth, but that description is almost too neat, too confident. Depth suggests a clear measurement, a bottom you can touch, a number you can write down and feel satisfied with. What we're really talking about is the point where the ocean stops behaving like a place and starts behaving like an idea. A region where familiar rules quietly give up and no one makes an announcement about it. It's strange to think that while we've photographed distant galaxies and landed machines on other planets, there is a part of our own world that remains mostly unseen. Not because it's far away, but because it's beneath us, hidden under layers of water that press harder the deeper you go. The ocean looks calm from the surface, reflective, sometimes playful. But beneath that surface is a vertical world stacked with invisible boundaries. And at the very bottom of that vertical world is something that feels less like a location and more like an ending, or maybe a pause. Before we sink any further into that thought, let me ask you something. Where are you listening from right now? Are you lying down, lights dimmed, screen glowing softly in the dark? Or are you sitting somewhere quiet, letting the day finally loosen its grip? And what time is it where you are? It's fitting to think about depth while the world around you slows, while clocks feel less important, while the surface noise fades just a little. If you find this space calming, or if you enjoy these slow explorations into places we don't often linger, consider liking the video or subscribing. It helps this small, quiet corner reach others who might be looking for the same gentle pause. There's no rush though. Nothing here demands urgency. Now, imagine standing on the edge of the Pacific Ocean. The water stretches out in every direction, a wide, restless surface that reflects the sky. Ships cross it. Storms pass over it. Sunlight dances on it. From here, it's easy to forget that the ocean is not just wide, but deep. Not deep in the casual sense, but deep in a way that resists imagination. Beneath that surface is a descent so gradual and so long that even the idea of falling doesn't quite apply. You don't drop into the deep ocean. You fade into it. The Mariana Trench begins like that. Not as a dramatic cliff or a sudden plunge, but as a slow, almost polite bending of the seafloor. The Earth's crust quietly slopes downward, inch by inch, kilometre by kilometre, until the concept of down becomes the only direction that matters. And the further you descend, the less the surface world feels relevant. Light thins, sound changes, time itself begins to feel different. Not because it actually changes, but because there are fewer reference points to anchor it. This is where the idea of an ending starts to creep in. Not an ending like a wall or a dead stop, but the kind where familiar things gradually stop accompanying you. First, waves are gone, then colour, then warmth. Then, eventually, even the idea of motion becomes abstract. The Mariana Trench isn't a place where the ocean suddenly ends. It's a place where the ocean keeps going long after you expect it to stop. What makes this especially unsettling is how close it all is. The trench is not hidden on the far side of the planet in some unreachable void. It's part of Earth's surface, folded inward like a quiet secret. You could fly over it in a few hours. Satellites pass above it constantly, and yet what lies below remains almost untouched. Not because we lack curiosity, but because the conditions themselves push back. As depth increases, pressure builds in a way that's difficult to explain without numbers, and numbers don't help much either. It's one thing to say that pressure increases steadily with depth, It's another to understand what that means when you're talking about thousands of meters of water stacked above a single point. Each layer adds its own weight, pressing down relentlessly. There's no pause, no relief. The deeper you go, the more the ocean insists on being noticed. And yet, despite that weight, life exists there. Not abundantly, not loudly, but stubbornly. The idea that something can survive where the ocean officially feels like it should end is one of the most unsettling and fascinating aspects of the trench. It challenges the quiet assumption that there is a limit beyond which existence simply gives up. The Mariana Trench does not offer that kind of certainty. When people first began to suspect how deep this place really was, the reaction wasn't awe so much as disbelief. Early measurements were inconsistent, rough guesses pulled from weighted lines and imperfect instruments. Each new attempt seemed to suggest that the ocean floor was farther away than previously thought. It was as if the bottom kept retreating every time someone tried to define it. That alone gives the trench a strange personality, one that doesn't like being pinned down. Even now, with advanced technology and precise instruments, the trench resists easy description. It's not a single pit or hole. It's a long, curved scar in the Earth's crust, stretching for hundreds of kilometers. Within it are slopes, ridges, and smaller depressions. There are places that are deep, and places that are deeper still. The deepest point, often mentioned by name, is less like a destination, and more like a reference, a marker humans have agreed upon so they can say, "This is as far as we know." But knowing is a flexible word here. We know the depth in the way we know the distance to a star, through instruments, through indirect measurement, through interpretation. Very few have seen it directly, and even fewer have lingered. Visiting the trench is not like exploring a cave or climbing a mountain. You don't move freely. You're enclosed, sealed inside layers of metal and glass, trusting that every joint, every bolt, will hold against forces that would crush an unprotected body instantly. And so the trench remains mostly theoretical in our daily lives. A statistic, a factoid, something mentioned in documentaries and trivia questions. But when you slow down and really consider it, the Mariana Trench becomes something else entirely. It becomes a reminder that the Earth still contains places that do not care about human presence, places that do not accommodate us naturally, places that require us to bring our own air, our own warmth, our own fragile bubble of survivability. That idea can be uncomfortable, but it can also be grounding. There is something oddly reassuring about knowing that the planet is not fully domesticated, not entirely mapped, not completely understood. The trench exists whether we think about it or not. It remains dark, pressurized, and patient, indifferent to surface concerns. As we move forward from here, we'll begin to unpack what it actually means to call a place the deepest on Earth. We'll look at how humans try to measure something that seems determined to evade simple measurement, and what happens to the senses as depth increases and familiar cues disappear. But for now, it's enough to sit with the idea that somewhere beneath the calm surface of the ocean, the world keeps descending long after the idea of an ending feels reasonable. There is no sudden shift yet, no dramatic plunge, just a slow, steady movement downward, where the ocean grows heavier, quieter, and more insistent with every passing meter. There is something quietly unsettling about the idea that the Earth has a bottom. Not a symbolic one, not a metaphorical edge, but a physical place where downward motion finally runs out of options. We are used to thinking in terms of surfaces. The ground beneath our feet, the surface of the sea, even space, which we imagine as vast and endless, still begins with looking up. Downward, on the other hand, rarely holds our attention for long. We dig a little, we build foundations, we drill, and then we stop. The Mariana Trench challenges that habit in a way that feels almost personal. When people say it is the deepest place on Earth, what they often mean is that it represents the last point where down still has meaning. Beyond it, there is no further descent available within the planet's natural surface. It is not a hole in the way a cave is a hole. It is not an absence of material. It is part of the Earth's skin, folded inward under its own slow, relentless forces. And yet, calling it a bottom feels strange, because nothing about it feels finished. The idea of a bottom usually suggests stability, a final resting place, something solid and reliable. The trench offers none of that comfort. It is narrow compared to the oceans that surround it, steep in places, sloped in others, and shaped by tectonic forces that continue to act on it even now. It exists because one part of the Earth's crust is sliding beneath another, a process so slow that it feels timeless, yet so powerful that it reshapes continents over millions of years. The trench is not a static landmark. It is an ongoing motion captured mid-act. What makes it especially difficult to grasp is that it does not announce itself. There is no visible border on the ocean's surface, no sign that says you have arrived above the deepest place on the planet. Ships pass over it without noticing. Storms rage above it without disturbing its silence. Sunlight sparkles on the waves directly above a depth that would crush nearly anything we know. From above, the ocean gives nothing away. This disconnect between appearance and reality is part of what makes the trench feel like an ending that refuses to look like one. If you were to stand on land at the edge of a cliff, your body would respond immediately. Your balance would adjust. Your breath might change. Height announces itself through sensation. Depth does not work the same way. You can be floating above nearly 11 kilometers of water and feel no different than if you were floating above a few meters. The body has no instinctive alarm for vertical distance below the surface. That absence of warning allows the mind to ignore what lies beneath. Most of the time, we do. We think of the ocean as something wide, not something tall. We measure it across maps, not down through layers. The trench forces a different perspective. It reminds us that the planet is not just spread out horizontally, but stacked vertically in ways that defy everyday intuition. Calling the trench the last place on Earth with a bottom also raises an uncomfortable question. Why does the idea of a bottom matter so much to us? Part of the answer is psychological. Humans are boundary-seeking creatures. We like edges. We like limits. They help us organize the world. The horizon gives us a sense of distance. Coastlines tell us where land ends and sea begins. A bottom suggests completeness. Without one, descent feels endless, and endlessness is hard to live with. For centuries, the ocean was assumed to be effectively bottomless. Sailors dropped weighted lines and failed to reach the seafloor. Early maps simply faded into blankness where knowledge ran out. This was not just a technical limitation. It shaped how people thought about the sea. A bottomless ocean felt unknowable, even threatening. Myths flourished in that uncertainty. Creatures were imagined. Abysses were feared. The unknown invited stories. The discovery that the ocean did in fact have a bottom was not comforting in the way one might expect. Instead of bringing closure, it introduced scale. The bottom was not close. It was far beyond what seemed reasonable. Far enough that reaching it became its own challenge, separate from understanding it. Knowing there was a bottom did not make the ocean feel smaller. It made it feel deeper in a more unsettling way. The Mariana Trench sits at the extreme end of that realization. It is the point where the ocean floor dips lower than anywhere else. Not because the ocean itself is uniquely deep there, but because the Earth's crust bends downward more sharply. The ocean is simply filling a space that the planet has created. That distinction matters. The trench is not carved by water, it is occupied by it. This means that even if the ocean were removed, hypothetically drained away, the trench would remain as a scar in the Earth's surface. A long curved depression shaped by geological forces that have nothing to do with waves or tides. In that sense, the bottom of the ocean is also the top of the Earth's interior processes. It is a boundary between two systems, one fluid and one solid, interacting constantly but operating on different timescales. Thinking of the trench as a bottom also implies a certain finality, but finality does not apply well here. The trench is not the deepest place the Earth could ever form. It is simply the deepest place that exists right now. Tectonic plates continue to move. Subduction zones shift. Over millions of years, depths change. New trenches can deepen. Old ones can fill. The bottom is temporary, even if it feels permanent on a human timeline. There is also a quiet irony in calling it the last place with a bottom when so few humans have ever been there. We name it, we measure it, we categorize it, but our presence there is fleeting and artificial. A brief visit inside a pressure-resistant shell does not make a place familiar. It barely makes it known. And yet the idea of a bottom continues to pull at our curiosity. There is something compelling about knowing that there is a place below which you cannot go without leaving the surface of the planet altogether. Space offers infinite outward expansion. The trench offers a final inward descent. One points away from Earth. The other leads directly into its quietest, most inaccessible expression. It is also worth noticing how language struggles here. We talk about depth as if it were distance, but depth carries emotional weight that distance does not. You can be far away without feeling threatened. Depth suggests immersion, pressure, enclosure. Saying that the trench is deep feels different from saying it is far down. One invites awe, the other invites unease. The trench sits beneath nearly the entire mass of the ocean. Every wave, every current, every drifting particle contributes to the weight pressing down on it. That pressure is not dramatic in motion, but it is absolute in presence. It does not surge or retreat. It simply exists, constant and unyielding. This makes the bottom of the ocean less like a floor you could stand on, and more like a condition you must endure. This reframes the idea of a bottom entirely. On land, a bottom is something that supports you. In the trench, the bottom is something that challenges your right to be there at all. It is not a resting place. It is a test. Despite this, life exists there, and that fact complicates everything. If the bottom were truly an ending, nothing would survive. But organisms do survive, adapted in ways that feel almost defiant. Their presence suggests that the bottom is not a hard limit, but a transition into a different mode of existence. One where energy is scarce, light is absent, and pressure is simply a given. This raises another uncomfortable thought. If life can exist at the very bottom of the ocean, then the idea of too deep is not universal. It is a human judgment based on our own limits. The trench is hostile to us, but not to everything. In that sense, calling it the last place on Earth with a bottom reveals more about human perspective than planetary reality. Still, the label persists because it satisfies something in us. It gives us a reference point, a place to say, this is as far as it goes, even if that statement is provisional, even if it only holds true until we learn more. As we continue downward in thought, the question shifts slightly. If this is the bottom, how do we know? How did we decide that this particular point deserves that title? Measuring depth in a place that resists presence is not straightforward, and the methods used tell their own story about human ingenuity and uncertainty. That story unfolds not in dramatic leaps, but in careful attempts, corrections and revisions. Lines lowered into darkness, echoes bounced off unseen surfaces, instruments adjusted for conditions they were never meant to face. Each measurement brought humans closer to defining the bottom, not as an abstract idea, but as a specific place with a number attached to it. But numbers, as we'll see, have their own limitations when applied to a place like this. Depth can be quantified, but understanding what that depth means is another matter entirely. And as the desire to define the bottom grew stronger, so did the realization that the ocean does not yield its secrets easily, especially when they lie beneath miles of crushing water. So while the Mariana Trench may be described as the last place on Earth with a bottom, that description is less of a conclusion and more of an invitation. An invitation to look closer at how we measure, how we define limits, and how the planet quietly ignores our need for neat endings. Trying to measure the deepest part of the ocean sounds at first like a straightforward task. You find the bottom, you measure the distance to it, and you write the number down. That logic works well on land. It works reasonably well in shallow water. It even works in space, where distances are vast but conditions are forgiving. The Mariana Trench exists in a category where those assumptions quietly fail. Measuring it has never been a simple act of reaching down and touching something solid. It has always been an exercise in approximation, correction, and humility. The difficulty begins with the fact that humans cannot go there easily, and for most of history could not go there at all. Before technology allowed us to send instruments into the deep, people relied on methods that now feel almost naive, though they were the best tools available at the time. Early sailors attempted to measure ocean depth by lowering weighted ropes over the side of ships. The idea was simple. You lower the rope until it stops paying out, then measure how much you've used. In shallow coastal waters, this worked well enough. In the open ocean, it often failed entirely. The rope would keep descending, disappearing into the water until it either snapped under its own weight or drifted sideways with currents, never quite reaching the bottom. Even when it did make contact, the rope could stretch, sway, or pile up on uneven terrain. Sailors were left with numbers that varied wildly from one attempt to the next. Some measurements suggested staggering depths. Others suggested impossibly shallow ones. The ocean refused to give a consistent answer. For a long time, this uncertainty was simply accepted. The deep ocean was considered unknowable, and exact measurements were not essential to daily life. Ships floated, ports functioned, trade continued. Knowing whether the ocean was 5 kilometers deep or 10 did not change much at the surface. Curiosity existed, but it was not yet paired with the tools needed to satisfy it. That began to change in the 19th century, when scientific interest in the oceans increased. Expeditions were launched not just to cross the seas, but to understand them. Weighted lines became heavier, reinforced with metal wire instead of rope. Winches replaced hand labour. Measurements improved, but the core problem remained. The deeper the water, the more the measuring tool itself became part of the challenge. A line long enough to reach the bottom was also long enough to introduce errors through drag, stretch, and drift. When early expeditions attempted to measure what we now know as the Mariana Trench, the results were confusing. Some readings hinted at extreme depth, but there was no reliable way to confirm them. The bottom seemed to retreat every time someone tried to define it. This wasn't because the trench was changing, but because the methods were still too blunt for the task. The real shift came with the development of echo sounding in the early 20th century. Instead of physically reaching the seafloor, scientists began to measure it indirectly using sound. The principle was elegant. A sound pulse is sent downward from a ship. It travels through the water, strikes the seafloor, and reflects back upward. By measuring the time it takes for the echo to return and knowing the speed of sound in water, you can calculate the depth. This method transformed oceanography almost overnight. Suddenly, large areas of the seafloor could be mapped without ever touching them. Depths that once took hours or days to estimate could be measured in seconds. The ocean began to reveal its contours, slopes, and trenches in ways that had never been possible before. But even echo sounding struggled when applied to the deepest parts of the ocean. The speed of sound in water is not constant. It changes with temperature, pressure, and salinity. Near the surface, sound behaves differently than it does several kilometers down. If those variations are not accounted for, depth calculations can be significantly off. A small error in sound speed, multiplied over thousands of meters, can lead to depth estimates that differ by tens or even hundreds of meters. In shallower regions, these discrepancies are manageable. In the Mariana Trench, they become magnified. Sound waves must travel through layers of water with dramatically different conditions. The deeper they go, the more pressure compresses the water, altering how sound moves through it. To correct for this, scientists need detailed profiles of the water column, which themselves require careful measurement. Measuring depth, it turns out, depends on measuring many other things first. Even with these corrections, early sonar-based estimates of the trench varied. One expedition would report a certain depth, another would find something deeper or shallower nearby. The question emerged quietly but persistently. Where exactly is the deepest point, and how do we know when we've found it? Part of the problem lies in how we imagine the bottom. It is tempting to picture a single, clean, low point, like the centre of a bowl. The reality is more complicated. The trench floor is not flat. It is uneven, with slopes, ridges, and smaller depressions scattered along its length. Finding the deepest point requires not just a single measurement, but extensive mapping across a wide area. Miss the deepest spot by even a few hundred meters horizontally, and your depth reading could be significantly different. As technology improved, so did the resolution of these maps. Multi-beam sonar systems allowed ships to send out multiple sound pulses at once, creating wide swathes of depth data. This revealed the trench in greater detail, showing its complex shape rather than a simple line on a chart. With each new survey, the picture sharpened, but it also became clear that the trench was more intricate than expected. At this stage, the challenge was no longer just measurement, but definition. What qualifies as the deepest point? Is it the single lowest spot measured so far? Is it an average across a region? Is it something that could change as instruments become more precise? The ocean does not provide a definitive answer. It allows only better approximations. Direct visits to the bottom added another layer to this effort. When submersibles finally reached the deepest known parts of the trench, they carried instruments designed to confirm depth readings. These missions were rare and risky, and each one became a milestone. Yet even then, precision was limited. Pressure affects instruments. Temperature affects materials. The very environment being measured interferes with the act of measurement. A submersible descending into the trench experiences increasing compression. Its hull flexes slightly. Its sensors respond to conditions they were calibrated for only imperfectly. Even determining the exact moment when the vehicle touches the bottom can be ambiguous. Is it resting on solid ground or sinking into soft sediment? The seafloor at these depths is not rock in the familiar sense. It is often fine-grained mud, slowly accumulating from particles that drift down from the surface over centuries. This means that the bottom is not always a clear boundary. It can shift slightly as sediments move. It can compress under weight. Two visits to the same location might register slightly different depths, not because the trench has changed in any meaningful way, but because the measuring conditions are never identical. All of this contributes to a peculiar situation. We speak confidently about the depth of the Mariana Trench, yet that confidence rests on layers of interpretation. The number we quote is the best estimate available at the moment, derived from a combination of sonar data, water profiles, and direct observation. It is not a fixed truth carved into the planet. It is a consensus built from imperfect tools. This does not make the measurement meaningless. On the contrary, it highlights the care and effort required to approach accuracy in extreme environments. Measuring the trench is not about arriving at a final number. It is about refining our understanding incrementally, knowing that each improvement brings us closer, but never all the way. There is also a philosophical aspect to this struggle. Humans have a deep attachment to numbers. Numbers feel authoritative. They suggest control. Saying that the trench is approximately 11 kilometers deep feels reassuring in a way that saying very deep does not. But the process of measurement reveals that the number is less a declaration and more a conversation between the observer and the observed. The trench resists being pinned down because it exists at the edge of our technological reach. Every attempt to measure it pushes instruments to their limits. Cables strain, electronics are tested, materials behave differently under pressure. Each expedition becomes not just a scientific mission, but an experiment in whether our tools can survive long enough to tell us anything useful. There is also the matter of scale. Measuring something so deep compresses human intuition. On land, we can walk distances, climb heights, and relate them to our bodies. Depth in the ocean offers no such reference. 11 kilometers is not something we can feel. It is not something we can visualize easily. We rely entirely on abstraction, on instruments translating physical reality into numbers we can manipulate. This reliance creates a subtle distance between knowledge and experience. We know how deep the trench is without knowing what that depth feels like. Even those who have visited it experienced it indirectly, through thick walls and small windows, insulated from the surrounding pressure. The measurement exists independently of sensation, and yet the act of measuring continues, driven by a quiet insistence that understanding matters even when it changes nothing practical. Knowing the depth of the trench does not make navigation safer. It does not improve weather forecasts. It does not directly benefit daily life. It satisfies a deeper impulse, the desire to know where the edges are, even if we never plan to go there ourselves. As instruments become more precise, measurements continue to be refined. Satellites now contribute indirectly by measuring variations in sea surface height, caused by gravitational differences in the Earth's crust below. These subtle bulges and dips in the ocean surface hint at structures beneath, including trenches. Combined with sonar data, they offer another layer of insight, another way of cross-checking what lies hidden. Despite all this, the trench retains its reputation as a place that refuses to be neatly defined. Its depth is known within a range, not as a single immutable value. Its shape is mapped, but never fully captured. Its bottom is identified, but always with the understanding that future measurements could revise what we think we know. This refusal is not antagonistic. It is simply the nature of extreme environments. The deeper we go, the more our tools become part of the equation. Measurement becomes an interaction rather than a passive observation. The trench does not hide itself. It simply exists on its own terms. As we move forward, this becomes increasingly important. Measurement is only the first step. Understanding what those depths mean for light, pressure, sound, and life requires accepting that precision has limits. The numbers tell us where we are. They do not tell us what it is like to be there. And as depth increases, familiar references begin to fall away. Light thins, temperature drops, and the ocean starts to behave in ways that feel less like water and more like a compressive force. Measuring depth is how we know where we are. Experiencing depth is something else entirely. That shift, from numbers to conditions, from measurement to environment, is where the story naturally drifts next. Sunlight feels so reliable at the surface that it's easy to forget how fragile its reach really is. We wake by it, schedule our days around it, complain when it's too bright or miss it when it's gone. It gives the world edges, colour and reassurance. Above the ocean, it reflects endlessly, turning waves into shifting mirrors. From that vantage point, it's tempting to believe that light fills the sea the way it fills the sky, thinning gradually but never truly leaving. The reality is far less forgiving. The disappearance of sunlight in the ocean is not sudden. There is no single moment where brightness switches off. Instead, light fades patiently, layer by layer, as though the water itself is gently absorbing it, keeping it, and refusing to give it back. The descent from brightness to darkness happens slowly enough that, if you were moving downward at the right pace, you might not notice the change at first. Your eyes would adjust, colours would dull, contrast would soften. The world would not announce what it is becoming. Near the surface, sunlight behaves much as it does on land. Reds, yellows and blues are all present, scattering and reflecting off particles, plankton and ripples. The water appears blue not because blue light is added, but because other wavelengths are already beginning to disappear. Red light is the first to go. Within just a few meters, reds are absorbed almost entirely. Objects that are red at the surface turn grey or black when viewed slightly deeper. This loss happens quietly and early, long before the ocean feels deep. As you descend further, orange and yellow wavelengths follow. The palette narrows, greens linger a bit longer, and blues persist the deepest. This is why deep water often appears blue or blue-green when illuminated. It's not that blue light thrives there, it's simply the last one standing. By the time you reach a few hundred meters, even blue light is struggling. Sunlight no longer behaves like illumination. It becomes more like a memory. This gradual filtering creates zones that scientists use to describe light availability, but the zones themselves are not strict boundaries. They blur into one another, much like twilight on land. The uppermost layer, where sunlight is strong enough to support photosynthesis, feels familiar in concept even if the environment is foreign. This is where most marine life congregates, where plants and algae can still convert light into energy. It is noisy, active, and busy by ocean standards. Below that, light weakens to the point where photosynthesis becomes impossible. Life does not stop, but it must change strategies. Energy now comes from falling debris, chemical reactions or predation rather than sunlight. This transition does not occur at a precise depth everywhere. It depends on water clarity, latitude, and season. The ocean resists uniformity even in how it loses light. As depth increases, the directionality of light also changes. Near the surface, sunlight comes from above at many angles, scattered by waves and particles. Deeper down, it becomes increasingly vertical, a faint glow filtering straight from overhead. Shadows sharpen briefly and then dissolve entirely as illumination becomes too weak to define shape. Eventually, the concept of shadow itself loses meaning. By the time you approach the deeper regions leading toward the trench, sunlight is no longer something you see. It is something you know is gone. Darkness here is not the absence of vision caused by closed eyes or a switched-off lamp. It is a physical condition created by distance, absorption, and water's quiet efficiency at stealing photons. Even the clearest ocean water cannot transmit sunlight indefinitely. Water is not empty space. It is dense, active, and constantly interacting with light. What makes this especially unsettling is how absolute the darkness becomes. On land, true darkness is rare. Even at night, starlight, moonlight, or distant city glow provide some reference. In the deep ocean, none of that exists. Starlight cannot penetrate kilometers of water. Moonlight fades even sooner. The darkness at depth is not dimness. It is total. This absence changes everything. Vision, which dominates human perception, becomes largely irrelevant. Eyes, if they exist, must adapt radically. Some organisms evolve enormous eyes to capture the faintest traces of light from above or from bioluminescent neighbours. Others abandon eyes entirely, relying on touch, vibration, or chemical cues. Darkness is not just a lack of light. It is a selective pressure that reshapes biology. Approaching the depths associated with the Mariana Trench, sunlight has long since vanished. Not thinned, not weakened. Gone. No dawn ever reaches these depths. No dusk ever settles. Time, as marked by light, ceases to exist. Day and night become surface concepts, irrelevant to the environment below. This has profound implications for how life experiences time. At the surface, light cycles regulate behavior. Organisms rise and sink, hunt and hide, bloom and rest according to the sun's schedule. In the deep, those cues disappear. Rhythms persist, but they are driven by other signals, often subtle and indirect. Some deep-sea creatures still respond to surface light cycles, not because they see the light, but because the behavior of prey above them changes with the time of day, sending pulses of activity downward. The loss of sunlight also alters temperature, but not in the way one might expect. After a certain depth, the ocean becomes uniformly cold. Seasonal warming at the surface does not penetrate far. Without sunlight to add energy, the water settles into a stable, near-freezing state. This stability is deceptive. It feels calm, but it is sustained by immense pressure and isolation. Darkness in the trench is not empty. It is filled with suspended particles drifting organic matter and slow movements that would be invisible even if light were present. The absence of sunlight does not mean the absence of motion. It simply means that motion cannot be seen without artificial illumination. This distinction matters because it shapes how humans interpret the deep. Darkness invites assumptions of stillness that are not entirely accurate. When submersibles descend into these depths and switch on their lights, the effect is often startling. Creatures appear suddenly, reflecting beams in unexpected ways. Particles swirl like snow in headlights. The seafloor emerges not as a dramatic landscape, but as a muted, textured expanse. The light reveals, but it also disturbs. Many organisms react immediately, retreating or freezing. Some have never encountered such brightness before. Artificial light in the trench is a foreign intrusion. It does not mimic sunlight. It creates harsh contrasts, sharp edges, and unnatural shadows. It reveals only what falls within its narrow cone. Beyond that cone, darkness remains complete. This reinforces the sense that the trench is not meant to be seen in the way we are accustomed to seeing. Visibility there is borrowed, temporary and controlled. There is also a psychological dimension to prolonged darkness. Humans are not built for environments without light. Even brief periods of darkness can alter mood, perception, and time awareness. In the trench, darkness is not something you endure until morning. There is no morning. For those few who have visited the deepest parts, the awareness that sunlight is impossibly far away can be disorienting, even through layers of technology. This awareness shifts attention inward. Without visual cues, the mind becomes more sensitive to sound, vibration, and eternal sensation. In the deep ocean, sound travels farther than light ever could. Darkness makes hearing more important, both for organisms that live there and for humans attempting to understand it. The disappearance of sunlight sets the stage for a world where sound, not sight, becomes the primary carrier of information. It is worth noting that the loss of sunlight is not unique to the trench. It happens everywhere in the ocean given sufficient depth. What makes the trench different is how far this process goes. There is no gradual reintroduction of light, no reflected glow from below. The darkness is final in a way that feels absolute. The bottom does not glow, it does not shimmer, it waits. This has led to a persistent misconception that the deep ocean is lifeless because it is dark. Darkness in human experience often signals absence of activity, absence of safety, absence of interest. In reality, darkness in the ocean is simply another condition to adapt to. Life does not require light itself, it requires energy. Sunlight is just one way of obtaining it. As sunlight disappears, other forms of light begin to matter. Bioluminescence becomes increasingly important as depth increases. Many deep-sea organisms produce their own light through chemical reactions. This light is not for illumination in the human sense. It is used for communication, camouflage, attraction, and defense. In a world without sunlight, light becomes a tool rather than a background condition. This transition from external to internal light marks a profound shift. Near the surface, light is something you exist within. In the deep, light is something you create, control, or avoid. Darkness becomes the default state, and light becomes intentional. This inversion changes how organisms interact and how ecosystems function. By the time one reaches the depths associated with the trench, even bioluminescence becomes sparse. Energy is limited, light is costly to produce. Many organisms rely instead on extreme sensitivity to pressure changes or chemical traces. Darkness is no longer dramatic, it is ordinary. The slow disappearance of sunlight is not just a physical process, it is a narrative one. It marks the transition from a world we recognise to one that feels increasingly alien. Each metre downward carries less visual information until eventually there is none. The ocean does not hide this from us. It simply does not compensate for our reliance on sight. Understanding this loss is essential for understanding everything that follows: pressure, sound, biology, and even human exploration are all shaped by the absence of light. The trench is not just deep, it is dark in a way that reshapes reality. And as light gives way to darkness, another force becomes impossible to ignore. The water itself, once merely a medium for light, begins to assert its weight. With every meter of descent, pressure increases steadily, relentlessly, turning depth into something that can be felt rather than seen. Pressure is not something humans are especially good at imagining. We understand it conceptually. We feel it in our ears during a flight or while driving down a mountain road. We notice it when a sealed bottle resists opening or when weather changes make joints ache. But these experiences are mild, brief, and easily escaped. Oceanic pressure, especially at extreme depth, is different. It is not an event. It is a condition. It does not come and go. It simply increases, steadily and without exception, the farther down you move. At the surface, pressure feels invisible because it is balanced. The weight of the atmosphere presses down on us constantly, but our bodies are adapted to it. We do not feel crushed because the pressure inside us matches the pressure outside. Water changes that balance almost immediately. Water is far denser than air, and it does not compress easily. Every meter of descent adds more mass above you, more weight that must be supported, more force pressing inward from all directions at once. This is where intuition begins to fail. On land, weight feels directional. Gravity pulls down. We stand on floors. We sit on chairs. Pressure in the deep ocean is not directional in that way. It comes from everywhere at once. There is no up or down in how it presses. It squeezes uniformly, wrapping around every surface, finding every weakness, exploiting every gap. There is no bracing against it. There is only withstanding it. To understand just how quickly pressure builds, it helps to think in increments that are small enough to grasp. For roughly every 10 meters you descend into the ocean, pressure increases by about 1 additional atmosphere. That means that at 10 meters, you're under twice the pressure experienced at sea level. At 20 meters, 3 times. At 100 meters, 11 times. This escalation happens quietly, invisibly, and without any dramatic signal. By the time you reach depths measured in kilometers rather than meters, the numbers become abstract. Hundreds of atmospheres, then thousands. At the deepest parts of the ocean, the pressure exceeds 1,000 atmospheres. That is the equivalent of having the weight of several large trucks pressing down on an area the size of a postage stamp. It is not a force that the human body can tolerate in any meaningful way. Unprotected, a human would not feel pain at those depths for very long. The body would be crushed before nerves had time to fully register what was happening. Air-filled spaces collapse first. Lungs compress. Ears rupture. Blood chemistry changes catastrophically. This is not because the ocean is hostile in an intentional sense. It is simply because pressure follows rules that do not care what is being subjected to them. What makes pressure in the deep ocean especially unforgiving is its consistency. Unlike waves or currents, pressure does not fluctuate dramatically. It does not offer moments of relief. Once you reach a certain depth, that pressure becomes the new normal. It presses just as hard whether you're moving or still, awake or asleep, present or absent. There is no shelter from it except through engineering. This is why exploration of the deepest ocean depends entirely on containment. Submersibles are not designed to resist pressure by fighting it outward. They are designed to distribute it evenly. Spherical or near-spherical shapes are common because they allow pressure to be shared across the structure, rather than concentrated at weak points. Even so, the materials used are pushed to their limits. Steel, titanium, and specialized composites are chosen not for comfort, but for survival. Inside these vessels, pressure is kept at levels humans can tolerate. The boundary between the interior and the surrounding ocean becomes a stark divide between safety and instant destruction. A window only a few centimeters thick separates breathable air from crushing force. This proximity is unsettling. The ocean does not need to break in dramatically. A small failure is enough. Pressure also alters the behavior of materials in subtle ways. Metals flex, seals compress, electronics behave differently, lubricants thicken. Components that work perfectly at the surface may fail unexpectedly at depth. Designing for these conditions requires not just strength, but predictability. Engineers must anticipate how materials will behave when subjected to forces far beyond everyday experience. Living organisms face the same challenge, but without the benefit of metal hulls or controlled environments. Life in the deep ocean does not resist pressure by building rigid shells in the way we might imagine. Rigidity is a liability under extreme compression. Instead, deep-sea organisms tend to be soft-bodied, flexible, and filled with fluids that match the surrounding pressure. This balance allows them to exist without being crushed. Cells at these depths are adapted to function under pressure that would disrupt the chemistry of surface life. Proteins fold differently. Enzymes are structured to operate efficiently when compressed. Membranes maintain integrity despite forces that would rupture ordinary cells. These adaptations are not dramatic in appearance, but they are profound in implication. They show that pressure is not inherently lethal. It is lethal only to those not built for it. One of the more unsettling realizations is that pressure does not feel like weight in the conventional sense. If you could survive unprotected at extreme depth, you would not feel heavier. Your limbs would not feel burdened. The pressure would be uniform, equal inside and out. The danger lies not in sensation, but in structural failure. The body is not designed to maintain internal equilibrium under such conditions. This uniformity is deceptive. It makes pressure feel abstract, even benign, until it is no longer balanced. A pocket of gas, a cavity, a sealed container suddenly becomes a site of concentrated force. The ocean exploits these imbalances instantly. There is no gradual adjustment. Failure happens all at once. Pressure also reshapes how sound travels. In dense, high-pressure water, sound waves propagate differently than they do near the surface. This makes sound an unusually effective means of communication and detection in the deep ocean. While light fades and disappears, sound carries, bending and travelling over long distances. Pressure helps make the deep ocean an acoustic environment rather than a visual one. This has consequences not only for marine life, but for human understanding. Many of the deepest regions of the ocean are known not through direct observation, but through sound-based measurements. Pressure shapes those measurements by influencing how sound behaves. Once again, the environment being studied becomes part of the method used to study it. There is also a temporal aspect to pressure that is easy to overlook. Pressure builds gradually during descent, but it is released rapidly during ascent. This imbalance can be dangerous even at much shallower depths. Divers are familiar with the risks of ascending too quickly, which can cause dissolved gases in the blood to form bubbles, leading to serious injury or death. At extreme depths, ascent is not even an option without controlled environments and long decompression schedules. In the deepest ocean, the idea of returning to the surface becomes less like a simple reversal and more like a complex negotiation with physics. Every meter upward changes conditions. Pressure decreases, gases expand, materials respond. Systems must adjust continuously. Descent may be steady, but ascent demands patience and precision. Pressure also affects perception in indirect ways. Knowing that you are surrounded by immense force alters how environments are interpreted, even when that force is contained. Those who have descended into the deep often describe an acute awareness of vulnerability, not because anything is actively threatening them, but because the margin for error is so thin. The ocean does not need to act. It only needs to be. This awareness can sharpen focus or induce unease. The mind becomes attuned to sounds, vibrations, small changes. A creak in the hull is no longer background noise. It is information. Pressure turns every sensation into a potential signal. At the bottom of the ocean, Pressure is not an extreme condition layered onto an otherwise familiar environment. It is the defining feature. Temperature, darkness, and chemistry all matter, but pressure is the constant that underlies them all. It shapes the physical structure of the seafloor itself, compacting sediments into dense layers. It influences geological processes, affecting how rocks fracture and how fluids move through the crust. Over geological timescales, pressure contributes to the transformation of materials in ways that are slow but irreversible. Sediments accumulate, compress, and eventually become rock. Organic matter is altered. Chemical reactions proceed along different pathways. The deep ocean is not static. It is active, but its activity unfolds under constraints that are difficult to observe directly. One of the most counterintuitive aspects of pressure is how normal it becomes to those adapted to it. For deep-sea organisms, pressure is not an obstacle to overcome each moment. It is simply the state of the world. There is no sensation of being crushed because there is no alternative. The body and environment are in equilibrium. Pressure, in that context, is invisible. This challenges the human tendency to frame extreme environments as inherently hostile. Hostility is relative. Pressure is only hostile when there is a mismatch between organism and environment. Where adaptation exists, pressure becomes background. Still, from a human perspective, pressure remains the primary barrier to exploration. Darkness can be illuminated, cold can be insulated against, distance can be travelled. Pressure cannot be negotiated with. It must be endured or excluded. This makes it a quiet gatekeeper, determining who and what can enter the deepest parts of the ocean. As exploration technologies advance, pressure continues to be the limiting factor. Each new record descent is not just a triumph of navigation, but a test of material science and engineering. The deeper we go, the less forgiving the margin becomes. Pressure does not scale linearly in terms of challenge. Each additional kilometre adds not just more force, but more complexity. Understanding pressure is essential for understanding everything that exists at depth. It explains why life looks the way it does, why exploration is rare, and why the deep ocean remains largely untouched. Pressure is not dramatic. It does not roar or surge. It presses steadily and without pause. As depth increases and pressure becomes the dominant condition, other senses begin to take precedence. Sight has already faded. Temperature has stabilized. What remains is a world defined by force and movement transmitted through dense water. In that world, sound becomes the primary way information travels, carrying signals across distances light can never reach. When light disappears, something else quietly takes its place. Not immediately, and not in a way that feels dramatic at first, but steadily enough that, over time, it becomes the dominant sense by default. In the deep ocean, sound is not a supplement to vision. It is the primary way the environment reveals itself. Where light fades into irrelevance, sound stretches outward, bending, travelling, and lingering in ways that feel almost unnatural to surface-bound intuition. At the surface, sound is fleeting. It dissipates quickly, scattered by air, absorbed by distance, interrupted by noise. We are accustomed to sounds having a clear source and a short lifespan. A voice fades as you walk away. A wave crashes and is gone. Silence returns easily. The ocean does not behave this way. Water carries sound far more efficiently than air, and the deeper you go, the more pronounced this difference becomes. This efficiency is not subtle. Sound in seawater can travel roughly 4 times faster than in air. It also travels farther, sometimes astonishingly farther. In the deep ocean, a single sound can propagate for hundreds, even thousands of kilometres under the right conditions. This is not because the ocean amplifies sound, but because it preserves it. There are fewer interruptions, fewer surfaces to scatter vibrations, fewer obstacles to dampen energy. Pressure plays a critical role here. As depth increases, water becomes denser and more uniform in temperature. These conditions create pathways that guide sound waves rather than dispersing them. In certain layers of the ocean, sound becomes trapped, bending back toward the center of the layer instead of escaping upward or downward. This phenomenon creates natural acoustic channels that act like invisible tunnels for sound. Within these channels, sound does not behave like a wave spreading outward in all directions. It becomes more focused, more persistent. A noise made in one part of the ocean can arrive somewhere else long after its source has stopped, altered slightly by distance but still recognizable. This turns the deep ocean into a place where echoes are not immediate reflections, but delayed arrivals from far away. For marine life, this is not a curiosity. It is the foundation of awareness. In darkness, where vision offers little to nothing, sound becomes the primary way to detect movement, locate prey, avoid predators, and communicate. Many deep-sea organisms are exquisitely sensitive to vibrations. Some can detect pressure changes caused by movement at distances that would seem implausible at the surface. Unlike light, sound does not require a clear line of sight. It bends around obstacles. It passes through darkness effortlessly. This makes it a reliable source of information in an environment where reliability is rare. Even the seafloor itself contributes to the acoustic landscape, reflecting and absorbing sounds in complex patterns that change with terrain. The deep ocean is not silent. It is simply quiet in a way that humans are not used to interpreting. There is no constant roar like wind or surf. Instead, there are intermittent signals, low-frequency rumbles from distant geological activity, sharp clicks from organisms using sound to sense their surroundings, long drawn-out moans produced by ice, tectonic movement, or shifting currents far above. Some of these sounds originate at the surface and travel downward. Storms generate noise that penetrates deep into the water column. Waves interacting with the seafloor create low-frequency vibrations that can be detected far below. Even rain leaves an acoustic signature, a pattern of sound that spreads outward and downward, changing character as it descends. Other sounds originate within the deep itself. Submarine landslides, slow shifts in sediment, or the movement of tectonic plates can produce signals that travel great distances through the water. These sounds are often too low in frequency for human hearing, but they are very much present. Instruments record them as steady pulses or sudden spikes, reminders that the seafloor is not as inert as it appears. Then there are biological sounds. Some deep-sea organisms produce clicks or pulses intentionally, while others generate noise simply by moving. The movement of fins, the snapping of jaws, the contraction of muscles all produce vibrations that travel through water. In a place where energy is scarce, sound production is often economical, brief, and purposeful. One of the most fascinating aspects of sound in the deep ocean is how it can create a sense of presence without visibility. Something can be there, near or far, without ever being seen. This uncertainty changes behavior. Organisms respond not to what they see, but to what they detect. A sudden vibration might signal danger. A rhythmic pattern might suggest a potential mate. Sound carries meaning in ways that light once did. For humans, this environment is disorienting. We are visually oriented creatures. When vision fails, we feel exposed. Descending into deep water, especially toward regions associated with the Mariana Trench, creates a sensory imbalance. The eyes offer little information. The ears, even though they are not adapted for underwater hearing, begin to pick up subtle cues through instruments and hull vibrations. Submersibles are never truly quiet. They creak under pressure. Systems hum. Water flows past the hull. Every sound is amplified by the awareness that silence would not mean safety, only absence of information. Those inside become acutely aware of noise, not because it is loud, but because it carries potential significance. Hydrophones, underwater microphones, extend human hearing into ranges and distances that would otherwise be inaccessible. Through them, scientists have learned that the deep ocean has its own soundscape, one that changes with location, depth, and time. Patterns emerge. Certain regions are consistently quieter, others are filled with low-frequency activity. One of the more unsettling realizations from these recordings is how much of the deep ocean's sound originates from human activity. Ship engines generate persistent noise that travels vast distances underwater. Sonar pulses, designed to detect objects, fill large volumes of the ocean with intense sound. Even activities far from the trench can influence its acoustic environment. This human-generated noise does not stop at the surface. It sinks, it spreads, it becomes part of the deep ocean's auditory background. For organisms that rely on sound for survival, this intrusion can be disruptive. Signals become masked, communication becomes harder. The deep ocean, once acoustically sparse, grows increasingly cluttered. Yet even with this intrusion, the ocean remains capable of producing sounds that defy easy explanation. Over the years, instruments have recorded noises that do not immediately match known sources. Some have later been attributed to ice movement, geological events, or previously undocumented biological activity. Others remain ambiguous, not because they are mysterious in a sensational sense, but because the environment is complex and poorly sampled. Sound in the deep ocean also behaves differently depending on frequency. High-frequency sounds attenuate quickly, losing energy and fading over shorter distances. Low-frequency sounds persist, travelling farther with less loss. This is why large-scale phenomena tend to dominate recordings from great depth. Small, sharp sounds disappear. Long, slow vibrations remain. This frequency bias shapes perception. The deep ocean feels dominated by slow, distant events rather than immediate ones. It creates an auditory environment that feels stretched, as though time itself is moving differently. Sounds arrive delayed. Their origins are unclear. Cause and effect are separated by distance and medium. For marine mammals that dive deep, this environment is navigated with precision. Some species use echolocation, producing sound pulses and listening for the returning echoes to map their surroundings. In darkness where light is useless, these echoes create a three-dimensional picture of space. Distance, size, and movement are encoded in sound. At extreme depths, however, even echolocation becomes less common. Energy costs increase. Prey becomes scarce. Many organisms rely instead on passive listening, detecting the sounds others produce rather than creating their own. Silence becomes a strategy rather than a lack. The seafloor itself plays a role in shaping sound. Its composition affects how vibrations are reflected or absorbed. Soft sediments dampen sound, harder surfaces reflect it. Variations in terrain create complex acoustic patterns that can confuse or clarify depending on perspective. Sound maps the deep in ways that vision cannot. From a human standpoint, sound has become one of the primary tools for exploring depths we cannot easily reach. Sonar mapping relies entirely on sound reflection. By sending pulses downward and measuring their return, scientists create images of the seafloor. These images are not photographs, they're interpretations of sound data translated into visual representations. This translation introduces another layer of abstraction. What we see of the deep ocean is often what sound tells us, converted into something our eyes can understand. The trench's shape, its slopes and ridges, are known largely through these acoustic reconstructions. Sound becomes sight by proxy. There is something fitting about this. In a place where light has no authority, knowledge arrives through vibration and echo. The ocean does not yield itself visually. It must be listened to. This requires patience, calibration, and an acceptance that clarity may never be complete. The deeper one goes, the more sound replaces other senses. Pressure transmits vibration efficiently. Darkness removes distraction. Temperature stabilizes. What remains is movement, and the information it carries. Sound becomes the thread connecting distant events, linking surface storms to deep currents, geological shifts to biological responses. This auditory dominance also affects how time is perceived. Sounds in the deep ocean are often slow, drawn out, repetitive. There is little urgency. Sudden noises stand out sharply against a background of gradual change. This contrast can heighten awareness, making the environment feel both calm and alert at the same time. For those listening through instruments, the deep ocean can feel strangely intimate. Sounds that originate far away arrive as whispers, reminders that the ocean is interconnected across vast distances. Nothing is truly isolated. A storm thousands of kilometers away leaves its trace. A ship passing overhead sends vibrations downward. The deep listens constantly. As exploration continues, sound remains indispensable. It is how we map, how we detect, how we monitor. It is how we know that the ocean is active even when it appears still. Sound reveals motion without revealing form, presence without visibility. Yet sound alone cannot tell the whole story. It hints, it suggests, it alerts. But it does not explain how organisms endure, how systems function, or how energy moves through a world without light. To understand that, attention must shift again, away from sensation and toward the living strategies that make existence possible under such conditions. And so, as the echoes stretch and fade, as vibrations carry information through darkness and pressure, the question naturally turns toward what listens in this environment. Not machines, not instruments, but life itself, shaped by the absence of light, the weight of water, and the constant murmur of the deep. There is a moment when learning about life in the deepest parts of the ocean, where the information stops feeling surprising and starts feeling contradictory. It is not just that organisms live there. It is that they live there without appearing to struggle. They do not look temporary or fragile. They look settled, adapted, and, in their own way, ordinary. This is where the phrase "should not exist" begins to reveal more about human expectations than biological reality. From a surface perspective, the deep ocean appears hostile in every measurable way. There is no sunlight. Temperatures hover just above freezing. Pressure is immense and unrelenting. Food is scarce and unpredictable. These are conditions that, taken together, seem incompatible with sustained life. And yet life is present, persistent and surprisingly diverse. Not abundant in the way a coral reef is abundant, but consistent enough to form functioning ecosystems. One of the first misconceptions to fall away is the idea that deep-sea life is rare because the environment is extreme. In reality, deep-sea life is widespread because the deep sea itself is vast. Most of the ocean's volume exists below the reach of sunlight. If life were absent there, it would mean that most of the planet's habitable space was empty. Evolution did not ignore that opportunity. The organisms that inhabit the deepest regions are not recent experiments. Many represent lineages that have persisted for millions of years, quietly adapting to conditions that change very slowly over time. The deep ocean is remarkably stable compared to surface environments. Temperatures fluctuate little. There are no seasons in the usual sense. Storms do not reach down. This stability allows for long-term specialization. What changes is not the environment itself, but the availability of energy. Without sunlight, life cannot rely on photosynthesis. Instead, it must make use of whatever arrives from above or emerges from within the earth. This has shaped deep-sea biology in fundamental ways. One of the primary food sources in the deep ocean is what is often called marine snow. This is not snow in the meteorological sense, but a slow, constant drizzle of organic particles falling from the surface. Dead plankton, fecal pellets, fragments of plants and animals all drift downward, sometimes taking weeks or months to reach the seafloor. By the time they arrive, much of their energy has already been consumed by organisms higher up. For deep-sea creatures, marine snow is both essential and insufficient. It provides a baseline level of nutrition, but rarely enough to support high activity or large populations. As a result, many deep-sea organisms have extremely slow metabolisms. They move little, they grow slowly. Some are thought to live for decades, possibly longer. Time, in this context, is not measured in days or years, but in long spans of survival under minimal input. In addition to falling debris, there are occasional large food falls. The most dramatic of these is a whale fall, when the carcass of a whale sinks to the seafloor. This sudden influx of organic material can support a localized ecosystem for years. Scavengers arrive first, followed by organisms that specialize in breaking down bone and extracting nutrients from the remains. These events are rare, but they represent significant pulses of energy in an otherwise sparse environment. Closer to tectonic activity, another energy source becomes available: chemical energy. In areas where fluids rich in minerals seep from the Earth's crust, specialized ecosystems form around chemosynthesis rather than photosynthesis. Microorganisms use chemical reactions to produce energy, forming the base of food webs entirely independent of sunlight. These systems demonstrate that light is not a requirement for life, only one option among several. As depth increases toward regions associated with the Mariana Trench, conditions become even more selective. Pressure increases beyond what most organisms can tolerate. Food becomes even scarce. Yet life does not vanish. It changes again. Many trench-dwelling organisms are small. This is not accidental. Smaller bodies experience less structural stress under pressure and require less energy to maintain. Large animals are rare, but not absent. What matters more than size is composition. Trench organisms tend to lack rigid skeletons. Bones, shells, and hard exoskeletons can become liabilities under extreme pressure. Soft tissues filled with fluid compress evenly, avoiding catastrophic failure. At the cellular level, adaptations are even more precise. Proteins, the molecular machines that drive life, behave differently under pressure. High pressure can cause proteins to unfold or lose their functional shape. Trench organisms produce proteins with structures that remain stable when compressed. Their cell membranes are composed of lipids that maintain proper fluidity under conditions that would rigidify or rupture surface-dwelling cells. These adaptations are not visible to the naked eye, but they are essential. Without them, life at depth would not function. Pressure does not merely threaten physical integrity, it interferes with chemistry. Trench organisms exist because their biochemistry has been tuned to operate under conditions that would disable most known life. One of the more striking discoveries in deep-sea biology is that many trench organisms are not fundamentally different from their shallow water relatives. They belong to familiar groups: crustaceans, worms, fish, microorganisms. What differs is not their basic plan, but the details of how that plan is executed. Evolution has not reinvented life for the deep, has modified it carefully. Fish living at extreme depths often lack swim bladders, which are gas-filled organs used by many fish to control buoyancy. At great pressure, gas-filled structures become unstable or impossible to maintain. Instead, deep-sea fish rely on body composition and subtle movements to maintain position in the water. Their tissues often contain compounds that help maintain buoyancy without relying on compressible gas. Eyes, when present, are often adapted for low-light detection rather than image formation. Some are large relative to body size, others are reduced or absent entirely. In complete darkness, eyes provide no advantage unless bioluminescence is involved. Even then, vision is limited to brief flashes and close-range interactions. Bioluminescence itself is widespread in the deep ocean, but less common in the deepest trench regions where energy is extremely limited. Producing light requires chemical resources. In the trench, where every molecule counts, many organisms conserve energy by abandoning light production altogether. Instead, they rely on other senses. Sensory hairs, pressure-sensitive structures, and chemical receptors are common. These allow organisms to detect movement, changes in water chemistry, or the presence of food without expending much energy. The environment does not reward speed or strength, it rewards sensitivity and efficiency. Reproduction in the deep ocean also follows different rules. Many trench organisms produce relatively few offspring, investing heavily in each one. Others release larvae that drift upward, developing in shallower waters before eventually descending. This vertical movement connects deep ecosystems to surface processes in subtle ways. The trench is isolated but not completely cut off. One of the most important points to understand is that deep sea life is not struggling constantly against its environment. It is not barely surviving, it is adapted. The conditions that seem extreme to us are normal to these organisms. Pressure is not felt as crushing. Darkness is not perceived as absence. Scarcity is expected, not alarming. This challenges a common narrative in which extreme environments are portrayed as lifeless or barely alive. In reality, they are simply different. The trench is not a place where life clings desperately to existence. It is a place where life operates according to a different set of constraints. Discoveries made during deep-sea expeditions often provoke surprise, not because the organisms are monstrous or alien, but because they are so matter-of-fact. A small amphipod scavenging along the seafloor, a translucent snailfish hovering just above the sediment, microorganisms quietly metabolizing chemicals in the mud. There is no spectacle, only persistence. This ordinariness is unsettling in its own way. It suggests that life does not require comfort, familiarity, or abundance. It requires only the right set of chemical and physical conditions, however narrow. Where those conditions exist, life follows. The presence of life in the trench also forces a reconsideration of limits. If organisms can survive at pressures exceeding 1,000 atmospheres, what does that say about the range of environments that could support life elsewhere? The deep ocean becomes a reference point not just for Earth, but for thinking about other worlds. It expands the definition of habitability. At the same time, it underscores how specialized life can become. Trench organisms are not generalists. They cannot survive at the surface. Pressure differences alone would kill them. Their adaptations bind them to their environment as tightly as they enable survival within it. The trench is not just where they live. It is what they are built for. Human exploration of these environments remains limited, but each visit reinforces the same conclusion. Life does not end where human comfort ends. It simply continues beyond it, reshaped and recalibrated. As we move forward, the focus naturally shifts from who lives there to where exactly they live. The seafloor itself, often imagined as a solid boundary, turns out to be something else entirely. Not a hard floor, but a shifting, layered environment that challenges even our basic assumptions about what a bottom looks like. Living without sunlight is difficult enough to imagine. Living without warmth adds another layer of discomfort. But living without time, or at least without the familiar signals that tell us time is passing, pushes the mind into unfamiliar territory. In the deepest parts of the ocean, all three conditions come together quietly. There is no light to mark a day, no warmth to suggest change, and no reliable rhythm to separate one moment from the next. Life persists anyway, not by ignoring these absences, but by reorganizing itself around them. At the surface, time is written everywhere. The sun rises and sets, shadows move, temperatures change, biological activity follows predictable cycles. Even when we are not paying attention, our bodies are. Hormones rise and fall, sleep arrives. Hunger follows schedules that have been shaped by millions of years of exposure to light and darkness. Time, for surface life, is something you live inside whether you acknowledge it or not. In the deep ocean, these cues are gone. There is no sunrise, no sunset, no seasonal warming or cooling. Temperature settles into a narrow range just above freezing and stays there. The water does not carry the memory of yesterday or the promise of tomorrow. It simply remains. This stability strips away many of the external signals that life elsewhere relies on to organize itself. For organisms living at depth, this means that time cannot be sensed in the usual way. There is no light-driven circadian rhythm, no daily cycle of activity and rest tied to the movement of the sun. Instead, biological processes slow and stretch. Growth happens gradually. Movement is deliberate. Energy is conserved not as a strategy, but as a necessity. Warmth, or rather the lack of it, reinforces this slow pace. Cold water holds less energy. Chemical reactions proceed more slowly. Muscles contract less efficiently. Everything that requires effort costs more relative to what is available. As a result, deep-sea organisms are not built for speed. They are built for endurance. Metabolism in the deep ocean operates at a different scale. Many organisms have metabolic rates far lower than those of their shallow water relatives. This does not mean they are weak or deficient. It means they are tuned to an environment where food is unpredictable and scarce. Burning energy quickly would be fatal in the long run. Survival depends on stretching limited resources across long spans of time. Some deep-sea animals can go months between substantial meals. When food does arrive, often in the form of drifting organic matter or the remains of larger organisms, it is used efficiently. Nothing is wasted. Growth spurts may occur briefly, followed by long periods of maintenance. This feast and famine pattern shapes behaviour and physiology alike. The absence of sunlight also affects how reproduction works. In surface environments, reproduction is often timed to seasons, light cycles, or temperature changes. In the deep ocean, these triggers are absent. Reproductive timing may instead depend on internal cues, food availability, or subtle environmental signals transmitted indirectly from above. Some species reproduce continuously at a low rate. Others rely on rare events, such as food falls, to support bursts of reproductive activity. Larval stages complicate this picture further. Many deep-sea organisms release larvae that drift upward into shallower waters where food is more abundant. There they grow and develop before eventually sinking back down as juveniles. This vertical migration introduces an indirect connection to surface time cycles. The larvae experience light, warmth, and daily rhythms even if the adults do not. In this way, surface time leaves a faint imprint on deep life without fully governing it. For organisms that remain entirely at depth, time becomes something internal rather than external. Biological processes unfold according to chemistry rather than clocks. Growth rates are slow but steady. Lifespans can be long, sometimes remarkably so. Without seasonal stress or frequent disturbance, there is little pressure to grow quickly or reproduce early. Longevity becomes a viable strategy. This challenges common assumptions about what a successful life looks like. In human terms, success is often associated with activity, productivity, and constant change. In the deep ocean, success looks like persistence. It looks like staying functional in a stable environment for as long as possible. It looks like patience encoded at the cellular level. The concept of time becomes even more abstract when considering the environment itself. The deep ocean changes, but on timescales that dwarf individual lives. Sediment accumulates millimetre by millimetre over centuries. Tectonic movements reshape the seafloor over millions of years. Chemical gradients shift slowly. For organisms living there, the world feels static not because nothing happens, but because changes occur too slowly to register meaningfully. This static quality has implications for behaviour. There is little reason to migrate horizontally. Food does not appear in predictable places. Light does not guide movement. Many organisms adopt a sit-and-wait approach, conserving energy until an opportunity arises. Others drift slowly, responding to faint chemical cues rather than visual landmarks. Without warmth, without light, and without obvious time markers, the environment encourages minimalism. Bodies are streamlined not for speed, but for efficiency. Organs that are unnecessary are reduced or lost. Eyes shrink or disappear. Pigmentation becomes irrelevant. What remains is what works. Temperature stability also affects how organisms cope with stress. On land and near the surface, temperature fluctuations can be a major source of physiological strain. Heat waves, cold snaps, and seasonal changes require constant adjustment. In the deep ocean, temperature is nearly constant. This reduces one source of stress while amplifying others, particularly pressure and scarcity. The combination of cold and pressure affects chemical reactions in ways that are still being studied. Enzymes must function under conditions that would denature surface proteins. Cellular membranes must remain flexible in cold, high-pressure water. These challenges are met through subtle molecular adaptations rather than dramatic structural changes. The absence of sunlight also means the absence of photosynthesis, which reshapes the entire energy economy of the deep. Energy arrives indirectly, often degraded by the time it reaches the seafloor. This creates a world where efficiency is paramount. Waste is minimized. Recycling is constant. Microorganisms play a crucial role in breaking down organic matter and making nutrients available again. In some regions, chemical energy supplements this sparse input. Chemosynthetic microbes use reactions involving sulfur, methane, or other compounds to produce energy. These processes are not tied to time cycles in the way photosynthesis is. They proceed as long as the necessary chemicals are present. This further decouples deep life from surface rhythms. When considering places like the Mariana Trench, this decoupling reaches an extreme. The trench exists far below the influence of surface conditions. Even large events above, storms, seasonal blooms, temperature shifts, arrive only as delayed diluted signals. A storm might increase the amount of organic matter sinking days or weeks later. A surface bloom might eventually result in slightly more marine snow. These are faint echoes, not direct experiences. This separation gives the trench a timeless quality. Not timeless in the sense that nothing changes, but timeless in the sense that change lacks urgency. There is no rush, no impending nightfall, no approaching winter. The environment does not pressure organisms to act quickly or often. For humans, this idea is deeply unsettling. We're used to time pushing us forward. Deadlines, aging, daily cycles all create a sense of movement. In the trench, that push is absent. If a human could exist there without harm, the psychological effects would be profound. Without external cues, the sense of duration would blur. Moments would lose definition. Even in controlled experiments on land, humans deprived of light cues quickly lose track of time. Sleep cycles drift. Perception changes. In the deep ocean, this deprivation is absolute. There is no accidental glimpse of light, no variation in temperature to hint at passing hours, only the steady presence of water and pressure. Deep-sea organisms are not disoriented by this, because they have never known anything else. Their biology is not built around external schedules, it is built around internal stability. Processes unfold at their own pace, guided by chemistry rather than clocks. This has led some scientists to describe the deep ocean as a place where time is stretched rather than stopped. Biological processes still occur, but they are slowed, elongated, and smoothed. There are fewer peaks and troughs, fewer dramatic shifts. Life continues in a low-frequency mode. Understanding this helps explain why deep-sea ecosystems can appear sparse but persistent. Population densities are low, activity is minimal. But extinction rates may also be lower because the environment does not fluctuate rapidly. Stability, even under extreme conditions, can be protective. There is also a philosophical dimension to this way of living. Without sunlight to define days, without warmth to suggest comfort, without time markers to impose urgency, life becomes less about progression and more about continuation. Existence is not a series of milestones. It is a steady state punctuated by rare events. Those rare events, food falls, geological disturbances, changes in chemical flow, become significant precisely because they are infrequent. When something happens, it matters. Organisms respond, energy is redistributed, then the system settles back into its slow rhythm. As exploration of the deep ocean continues, this slow rhythm challenges human expectations. We look for drama, for movement, for visible change. The deep offers something else. It offers persistence without spectacle. Living without sun, warmth, or time does not mean living without order. It means living according to a different order, one that does not align with surface experience. The rules are consistent. The constraints are clear. Life fits itself into the available space with remarkable precision. As attention shifts downward again, away from biology and toward the physical environment that supports it, another assumption begins to dissolve. The idea that there is a solid, stable floor waiting at the bottom of the ocean turns out to be misleading. The ground itself behaves in ways that challenge the notion of a simple boundary, revealing a sea floor that is anything but fixed. It is easy to imagine the bottom of the ocean as a kind of underwater ground, a solid surface where descent finally stops and stability begins. The word floor invites that assumption. Floors are flat. They support weight. They mark a clear boundary between above and below. In the deepest parts of the ocean, that expectation quietly falls apart. The seafloor, especially in regions approaching the Mariana Trench, is not a floor in any familiar sense. It is not firm, not still, and not particularly interested in behaving like a final surface. What exists at the bottom is better described as a transition zone than a boundary. It is where water meets sediment, where particles settle slowly from above, where geological forces from below continue to reshape the Earth's crust. It is a place of accumulation, compression, and movement, even though none of that movement is obvious at human timescales. Much of the deep sea floor is covered in fine-grained sediment rather than exposed rock. This sediment is the end result of countless small contributions, microscopic shells from plankton, fragments of organic matter, mineral particles carried by currents, volcanic ash from distant eruptions. Over time, these materials drift downward and settle, forming layers that can be surprisingly thick. The process is so slow that it defies intuition. A layer a few centimeters thick may represent thousands of years of accumulation. This slow accumulation creates a surface that is soft, compressible, and unstable. When something rests on it, it does not sit neatly on top. It sinks, sometimes gradually, sometimes unevenly. The idea of standing on the seafloor, even in imagination, becomes problematic. There is no firm ground to stand on. There is only material that yields under pressure. In trench environments, this effect is amplified. The slopes leading down into the trench funnel sediment toward the deepest points. Gravity pulls particles downward along the trench walls, adding to the accumulation at the bottom. Over time, this creates thick deposits of fine mud, compacted by pressure but still lacking the rigidity we associate with solid ground. This sediment behaves in ways that are unfamiliar. Under extreme pressure, water trapped between particles is slowly squeezed out. Layers compact. Chemical reactions occur. Organic material is altered. What begins as loose debris gradually transforms into denser material, eventually becoming rock over geological timescales. The seafloor is not static. It is in the process of becoming something else. Adding to this complexity is the fact that trenches exist at tectonic boundaries. The Mariana Trench in particular is formed where one tectonic plate is sliding beneath another. This process, known as subduction, means that the seafloor itself is moving, albeit very slowly. One part of the Earth's crust is being forced downward into the mantle, carrying sediment and water with it. This movement introduces instability. Earthquakes occur as plates grind past one another. These events can trigger submarine landslides, sending large volumes of sediment cascading downward. Such landslides can reshape parts of the seafloor abruptly, burying organisms and redistributing material. The bottom is not only soft, it is occasionally mobile. These events are rare on human timescales, but they matter. They remind us that the seafloor is not a finished product. It is a snapshot of an ongoing process. Even at the deepest point, the Earth is still rearranging itself. The chemistry of the seafloor further complicates the idea of a floor. Sediments are not inert. They host microbial communities that continue to process organic material long after it has settled. These microbes consume what little energy remains, altering the chemical composition of the sediment. Gases are produced, minerals are transformed. The boundary between living and non-living becomes blurred. In some places, fluids seep upward from beneath the seafloor, carrying dissolved chemicals. These seeps can create localized habitats where life thrives on chemical energy, rather than organic debris from above. The ground in these cases is not just a surface, it is a source. From a human perspective, the seafloor's lack of solidity presents practical challenges. Submersibles that reach extreme depths must account for the nature of the ground beneath them. Landing is not a simple matter of touching down. Vehicles can sink into soft sediment, tilt unexpectedly, or become partially buried. Instruments placed on the seafloor may shift over time, altering measurements. Even determining where the seafloor begins can be ambiguous. Sonar detects a reflective surface, but that surface may represent a change in sediment density rather than a hard boundary. Beneath it, additional layers may continue for meters before reaching more consolidated material. The bottom, detected by instruments, is often just the top of a gradual transition rather than a clear endpoint. This ambiguity challenges the notion of depth itself. When we say the trench is a certain number of meters deep, what exactly are we measuring to? The top of the sediment? The point where sediment becomes rock? The deepest depression in a shifting landscape? Each definition yields a slightly different answer. The seafloor resists precision because it does not offer a single, definitive surface. There is also a vertical dimension to the seafloor that is easy to overlook. It is not simply a flat expanse. It includes slopes, ridges, and smaller depressions. In trenches, these features can be steep and irregular. Gravity-driven processes continually reshape them, smoothing some areas while carving others. Over time, the seafloor becomes a record of countless small movements rather than a static platform. Life interacts with this unstable surface in subtle ways. Many deep-sea organisms live within the sediment rather than on top of it. Worms, microbes, and small invertebrates burrow through the mud, creating networks of tunnels. These movements alter sediment structure, affect chemical gradients, and influence how nutrients are distributed. The seafloor is not just shaped by geology, it is shaped by biology as well. These interactions occur slowly, but their cumulative effect is significant. Bioturbation, the process by which organisms rework sediment, can blur layers that would otherwise preserve a clear geological record. In the trench, where sedimentation rates are low and disturbance is infrequent, these biological processes become especially important in shaping the local environment. From above, the seafloor might appear calm and lifeless. Up close, it is quietly active. Particles settle, microbes metabolize, chemical gradients shift. The ground breathes in a way that is difficult to perceive but essential to understanding the system as a whole. The idea of a floor also implies a separation between environments. Above is water, below is ground. In the deep ocean, this separation is less clear. The seafloor releases chemicals into the water. The water deposits material onto the seafloor. Organisms move between the two, blurring the boundary. It is more accurate to think of the bottom as an interface rather than a barrier. This interface plays a crucial role in global processes. Sediments store carbon. Chemical reactions at the seafloor influence ocean chemistry. Over long periods, material subducted at trenches is recycled into the Earth's interior, eventually influencing volcanic activity elsewhere. The bottom of the ocean is not an endpoint. It is part of a planetary loop. Understanding this challenges the intuitive idea that the deepest point on Earth is a place where things stop. In reality, things continue there in different forms. Motion becomes slower, change becomes subtler, but nothing truly halts. For humans, this realization can be unsettling. We like clear boundaries. We like knowing when we have reached the end of something. The trench refuses to provide that closure. Even at its deepest point, the Earth continues downward, not in open space, but into itself. This lack of a true floor also affects how we imagine exploration. There is no place to plant a flag, no solid platform to claim. The bottom does not welcome occupation. It tolerates brief contact and then reasserts its own dynamics. Sediment shifts, pressure remains. The environment reminds visitors that they are temporary. As attention continues to drift through this environment, it becomes clear that the seafloor is not merely a backdrop for life. It is an active participant. Its softness, chemistry, and motion shape what can exist there and how. Life adapts not to a static surface, but to a moving, compressing, chemically active boundary. This perspective reframes the idea of depth once again. Depth is not just distance from the surface. It is immersion in a system where water, sediment, chemistry, and geology interact continuously. The deeper one goes, the less the world resembles a place, and the more it resembles a process. And within that process, there is something else quietly accumulating. Not just sediment, not just chemical gradients, but traces of human presence, carried downward from the surface and settling into places once thought unreachable. Even here, at the edge of the planet's downward reach, the influence of the surface world begins to appear in subtle and unexpected ways. There is no practical reason for humans to descend into the deepest parts of the ocean. No resources essential to survival wait there. No routes of travel depend on it. No civilizations are built near it. And yet, again and again, humans have looked at the depth of the ocean and felt something pull them downward. Not a need, but a desire. A quiet insistence that if a place exists, especially if it marks an extreme, someone should try to reach it. This desire does not come from comfort or familiarity. The deep ocean offers neither. It comes instead from a pattern that repeats throughout human history. When there is a boundary, humans want to approach it. When there is an edge, they want to see what lies beyond. The edge of continents led to ocean crossings. The edge of the atmosphere led to space flight. The deepest point on Earth represents another kind of edge, one that points inward rather than outward. What makes this urge particularly curious is that it persists even when the risks are obvious. From the earliest attempts to measure depth to the first crude descents into extreme environments, the dangers have been clear. Pressure, darkness, isolation, and the possibility of catastrophic failure are not abstract concerns. They are fundamental characteristics of the deep. Yet the desire to go lower remains. Part of this desire is rooted in curiosity, but curiosity alone does not fully explain it. Humans are curious about many things they never attempt to experience directly. Few people feel compelled to stand inside a volcano or beneath a collapsing glacier. The deep ocean, however, exerts a different kind of pull. It is hidden but present, inaccessible, but still part of the same world we inhabit. There is also a psychological dimension to depth that differs from height or distance. Heights challenge balance and fear of falling. Distances challenge endurance and navigation. Depth challenges containment. It asks whether humans can survive when surrounded completely, when there is no horizon, no visible exit, no immediate reference to the surface. Descending is not just movement, it is surrendering familiar control. Early attempts to reach greater depths were not dramatic expeditions. They were incremental, better ropes, heavier weights, more reliable winches. Each improvement allowed humans to probe a little farther into the unknown. The ocean responded not with revelation, but with silence. Lines disappeared into darkness. Measurements came back inconsistent. The bottom remained out of reach. As technology advanced, that silence became more provocative rather than discouraging. Sound-based measurements hinted at enormous depths. Charts showed trenches that seemed almost exaggerated. The idea that the planet contained a place so far below the surface that it defied ordinary measurement captured imaginations. The deep ocean began to feel less like a void and more like a challenge. The first serious attempts to physically descend into extreme depths required a shift in thinking. Humans could not adapt their bodies to pressure. They had to bring the surface with them. This meant building vessels that could maintain a pocket of familiar conditions inside an utterly unfamiliar environment. The deep ocean would not be negotiated with, it would be isolated from. This approach changed the nature of exploration. The goal was no longer to endure the environment directly, but to observe it through layers of protection. Thick walls, small windows, limited mobility. Descending into the deep became an exercise in trust, not in strength or skill. Trust in materials, trust in engineering, trust that every component would behave as expected under conditions it could never be tested in fully beforehand. The psychological challenge of this cannot be overstated. To descend thousands of meters beneath the surface is to place oneself in a situation where return depends entirely on systems functioning correctly. There is no swimming to safety, no rapid ascent, no external rescue. Once committed, the descent must be completed, and the ascent must follow its own careful path. Despite this, people volunteered. Scientists, engineers, explorers. Not because the deep promised reward, but because it promised understanding. Each descent offered the possibility of direct observation rather than inference, to see the seafloor rather than imagine it, to confirm measurements, to witness life where theory suggested it might exist. The desire to go lower also reflects something about how humans relate to extremes. Extremes provide context. Knowing the highest mountain, the longest river, the deepest ocean trench gives shape to our understanding of the planet. These reference points help define scale. Without them, the world feels less grounded, less complete. The deepest parts of the ocean, particularly those associated with the Mariana Trench, occupy a special position in this framework. They are not just deep, they are deeper than expected, deeper than intuition allows. Reaching them is not a matter of endurance, but of confronting limits imposed by physics itself. There is also a symbolic aspect to descending rather than ascending. Exploration narratives often focus on upward movement. Mountains climbed, skies crossed, space entered. Descending reverses that narrative. It is inward facing. It suggests introspection rather than conquest. Going lower feels less like claiming territory and more like approaching something that was always there, but deliberately avoided. This may explain why deep-sea exploration often carries a quieter tone than other forms of exploration. There are no flags planted triumphantly, no dramatic declarations of ownership. The deep does not lend itself to spectacle. It demands patience and humility. Even success feels subdued, almost private. Media portrayals of deep-sea descents often emphasize danger, but those who have made the journey describe something else, a sense of stillness, a narrowing of focus, a heightened awareness of small details. The world outside the vessel becomes abstract. Inside, attention turns to instruments, sounds, and the slow progression of depth readings. As descent continues, surface concerns lose relevance. Time stretches. Communication with the surface becomes delayed or minimal. The mind adjusts to a smaller world defined by the vessel's interior. This isolation can be unsettling, but it can also be clarifying. With fewer stimuli, attention sharpens. The descent becomes a form of enforced mindfulness. The desire to go lower is also reinforced by the fact that so few have done it. Rarity adds weight to experience. Knowing that only a handful of humans have seen a particular place firsthand imbues that place with significance beyond its physical characteristics. It becomes part of a shared human story of exploration, however small that chapter may be. This exclusivity is not about prestige in the usual sense. Deep-sea exploration does not bring fame comparable to spaceflight or polar expeditions. It brings something quieter, the satisfaction of having answered a question directly rather than indirectly. The knowledge that an abstract concept has been replaced by experience. There is also a sense of responsibility that accompanies this desire. Humans have altered nearly every accessible part of the planet. The deep ocean remains one of the few places where human presence is minimal. To go there is to observe without immediately altering, at least on a large scale. Exploration becomes documentation rather than exploitation. At the same time, the act of going lower carries an implicit acknowledgement that curiosity alone can justify intrusion. This raises ethical questions that are still being considered. Does observing justify disturbing? Does knowing justify risking damage to fragile environments? The desire to go lower must be balanced against the recognition that these environments have existed without us for millions of years. Technological advances have made descent more accessible but not routine. Each mission remains expensive, complex and risky. This scarcity forces selectivity. Only certain questions are pursued. Only certain locations are visited. The deep ocean is not surveyed casually. It is approached deliberately. This deliberateness shapes the kind of knowledge gained. Data from the deep tends to be precise but limited. Observations are detailed but localized. Broad patterns must still be inferred. The desire to go lower does not eliminate uncertainty. It reframes it. There is also an emotional component that is difficult to quantify. Standing, or rather hovering, above the deepest known part of the planet evokes a sense of scale that is hard to replicate elsewhere. It is not awe in the dramatic sense. It is a quiet recalibration. A reminder that human experience occupies a thin layer at the surface of something far larger. This recalibration can be humbling. It can also be grounding. The deep ocean does not respond to human presence. It does not reward bravery. It does not acknowledge achievement. It simply exists. To descend into it is to accept that existence does not require an audience. The desire to go lower persists because it answers a question that cannot be resolved from a distance. What is it like down there? Not in theory, not in models, but in reality. What does the water look like? How does the seafloor appear? What moves and what remains still? Even knowing that the answers will be subtle does not diminish the urge. If anything, it strengthens it. The deep ocean is not dramatic in the way popular imagination suggests. It is restrained, quiet, and sparse. To witness that restraint firsthand is to expand one's understanding of what a living planet looks like beyond the surface. As exploration continues, motivations evolve. Early descents were about reaching a record. Later ones focus more on observation and data collection. The desire shifts from being first to being thorough, from touching the bottom to understanding the environment. Yet the core impulse remains unchanged. Humans want to know where the limits are, not to stop there, but to acknowledge them. The deepest parts of the ocean offer a clear statement of constraint. Pressure will not be overcome by strength. Darkness will not be banished permanently. Distance will not be erased. The only way forward is careful adaptation. This makes the deep ocean a mirror of sorts. It reflects not our power, but our ingenuity and restraint. Going lower is not about dominance, it is about accommodation, about fitting into an environment temporarily without expecting it to change for us. As attention shifts from the motivation to the means, another layer of the story emerges. The desire to go lower would remain abstract without the machines designed to carry humans and instruments into places they cannot survive on their own. These machines are not just tools, they're intermediaries between worlds, translating pressure, darkness, and distance into something humans can engage with, however briefly. Machines were never meant to live where humans cannot. That may sound obvious, but it becomes especially clear when those machines are asked to descend into the deepest parts of the ocean. The abyss does not simply challenge living bodies, It challenges materials, assumptions, and the very idea that complex systems can function reliably under conditions that erase most margins for error. Every machine that dares the abyss is a compromise between what physics allows and what human curiosity demands. The earliest machines sent into deep water were not ambitious. They were simple, almost cautious. Weighted instruments lowered on cables, thermometers encased in protective housings, pressure gauges designed to survive longer than the rope holding them. These devices did not explore so much as they sampled, dipping into darkness and returning with partial answers. They were extensions of human hands, reaching down rather than moving freely. As depth increased, this approach reached its limits. Cables became liabilities. Their own weight introduced strain. Currents pushed them sideways. The deeper the water, the less control operators had over where instruments actually went. Precision was lost long before the bottom was reached. To go lower, machines would have to become autonomous in a way earlier tools were not. This realization led to a shift in design philosophy. Instead of lowering machines into the ocean, engineers began to imagine machines that could descend under their own control, survive independently, and return. This was not just an engineering challenge, it was a conceptual one. The ocean would no longer be something machines were dipped into. It would be something they entered. Pressure was the first obstacle. Any machine intended to reach extreme depths had to survive forces that would crush ordinary structures instantly. This eliminated most conventional shapes. Flat surfaces, corners, and seams become points of failure under uniform compression. Designers turned instead to spheres and cylinders, shapes that distribute pressure evenly and reduce stress concentrations. Materials choice became critical. Steel offered strength but added weight. Titanium provided strength with reduced mass but increased cost and fabrication difficulty. Composites promised new possibilities but introduced uncertainties about long-term behavior under pressure. Every material had trade-offs, and every trade-off mattered more the deeper the machine went. Inside these pressure-resistant shells, systems had to operate normally. Electronics needed to function without overheating. Power supplies had to be reliable. Control systems had to respond predictably. All of this had to happen in an environment that offered no opportunity for repair. A failure at depth could not be fixed. It could only be endured or result in loss. Buoyancy added another layer of complexity. To descend, a machine must be heavier than the water it displaces. To ascend, it must become lighter. Achieving this without relying on fragile mechanisms is challenging. Many deep-diving machines use expendable weights that can be released to trigger ascent. This approach is simple and reliable, but it means each dive is a one-way commitment until ascent is initiated. Navigation in the abyss is unlike navigation anywhere else. GPS signals do not penetrate water. Visual landmarks are absent. Currents can be subtle but persistent. Machines must rely on the inertial navigation systems, acoustic signals, and careful pre-planning. Position estimates accumulate error over time. Knowing exactly where a machine is becomes increasingly difficult the longer it remains at depth. Communication presents its own challenges. Radio waves travel poorly through seawater. Optical signals require clear lines of sight and short distances. Sound becomes the primary medium for communication, but sound is slow compared to radio and subject to distortion. Commands sent from the surface may take seconds to arrive. Responses take just as long to return. Real-time control is impossible. Machines must be trusted to operate semi-independently. This trust is not given lightly. Every system is tested repeatedly in shallower water before being allowed to descend further. Even then, testing can never fully replicate abyssal conditions. Pressure chambers simulate compression, but they cannot reproduce every aspect of the deep environment. At some point, machines must be committed to conditions that exceed anything they have experienced before. Crude submersibles represent the most complex and demanding category of abyssal machines. Unlike remotely operated or autonomous vehicles, they must support human life. This introduces constraints that no uncrewed system faces. Air must be breathable, temperature must be regulated, carbon dioxide must be removed. All of this must function flawlessly for the duration of the dive. The pressure hull of a crewed submersible is a marvel of engineering restraint. It must be thick enough to resist collapse, but not so thick that it becomes impossibly heavy. Viewports, if included, must be small, carefully shaped, and made of materials capable of withstanding immense force without cracking. Every opening becomes a potential weakness. Uncrewed machines have more freedom. They can be smaller. They can be simpler. They can take risks that would be unacceptable with human lives on board. As a result, they now perform much of the deep sea exploration. Autonomous vehicles map the seafloor, collect samples, and record data over long periods. They do not need to return immediately. Some are designed to stay at depth for months. These machines extend human presence without extending human vulnerability. They allow exploration to proceed incrementally, gathering information that informs future missions. Yet even they are not immune to the abyss. Pressure damages seals, corrosion attacks exposed components. Biofouling occurs even at great depth. The ocean finds ways to interact with every surface placed within it. One of the most striking aspects of abyssal machines is how quiet they must be. Noise can interfere with instruments. It can disturb marine life. It can mask the sounds researchers are trying to record. Motors are designed to operate smoothly. Movements are deliberate. Energy is conserved. The machine becomes a careful visitor rather than an intruder, at least as much as possible. Lighting systems present another compromise. Light is necessary for observation, but it alters the environment being observed. Many deep-sea organisms react strongly to illumination. Some flee, some freeze, some are drawn toward it. Designers must balance the need to see with the desire to minimize disturbance. Lights are often used sparingly, focused narrowly, and turned off when not needed. Sampling mechanisms introduce further complexity. Collecting a piece of the seafloor or a living organism requires interaction. Grippers must function reliably under pressure. Containers must preserve samples during ascent as pressure decreases. Chemical conditions must be maintained if delicate organisms are to survive. Each sample represents a chain of engineering challenges extending from the bottom of the ocean back to the surface. The history of abyssal machines is marked by failures as well as successes. Vehicles have been lost. Systems have malfunctioned. Communication has been severed. In some cases, machines simply vanished and never recovered, their final moments unrecorded. These losses are not treated lightly. Each represents not just financial cost, but lost data and unanswered questions. Yet failure has not discouraged continued effort. It has refined it. Designs improve. Redundancies are added. Materials are upgraded. Lessons are learned slowly, because opportunities to test them are rare. The abyss does not allow rapid iteration. Progress happens in careful steps. When machines do succeed, their contributions are often subtle rather than dramatic. A clearer map of the seafloor, a better understanding of sediment composition, a longer recording of ambient sound. These are not headline-grabbing achievements, but they accumulate. Over time, they transform ignorance into familiarity. One of the most profound effects of these machines is how they mediate human perception. Cameras transmit images that become the basis for our mental picture of the deep ocean. Sonar data is translated into visual maps. Sensor readings are graphed and analysed. The abyss becomes knowable not through direct experience but through layers of representation. This mediation shapes understanding. The deep ocean we imagine is the deep ocean as machines allow us to see it. What they cannot detect remains invisible. What they are not designed to look for goes unnoticed. In this sense, machines do not simply reveal the abyss, they define it. The relationship between humans and these machines is therefore intimate. Engineers and scientists must anticipate how machines will behave in environments they themselves cannot experience directly. They must imagine conditions, predict failures, and trust systems once deployed. The abyss tests not just technology, but foresight. As machines continue to improve, the boundary of exploration shifts gradually. Deeper, longer, more detailed missions become possible. Yet the fundamental challenge remains unchanged. Pressure, darkness, and isolation impose limits that cannot be engineered away entirely. Machines do not conquer the abyss, they negotiate with it. This negotiation produces moments of quiet significance. A camera settling gently onto soft sediment, a manipulator arm lifting a small sample, a sensor recording data in complete darkness. These moments are small, but they represent contact between worlds that rarely meet. Through machines, humans reach places they cannot inhabit. The machines endure conditions we cannot tolerate. Together, they form a fragile bridge across an otherwise impassable divide. The abyss does not yield easily, but it allows brief visits, measured interactions, and partial understanding. As these machines descend and ascend, carrying data rather than treasure, they reveal something unexpected. At the very bottom of the ocean, where pressure is greatest and light is absent, the environment is not empty. It contains surprises, some reassuring, some unsettling, waiting quietly for the next visitor capable of noticing them. When humans finally reached the deepest known parts of the ocean, there was an expectation, spoken or not, that something extraordinary would reveal itself immediately. Not necessarily monsters or dramatic landscapes, but at least something unmistakably different. Something that would announce without ambiguity that this place was unlike any other on Earth. What was found instead was quieter, subtler, and in many ways more unsettling than spectacle would have been. The very bottom does not announce itself with grandeur. There is no sharp edge, no dramatic drop-off that signals arrival. Descent readings slow, instruments stabilize. Eventually the downward motion stops, not because the environment has changed abruptly, but because there is nowhere further to go without entering the Earth itself. The deepest parts of the Mariana Trench do not feel like a destination. They feel like a pause. The seafloor at these depths is often described as flat, but that word is misleading. It is flat only in comparison to steep trench walls. In reality, it is uneven, textured by fine sediment, marked by small ridges and depressions that become visible only under artificial light. The ground does not glitter or reflect. It absorbs light, giving back only muted tones of grey and brown. Colour, where it exists at all, comes from organisms rather than the environment itself. One of the first and most significant discoveries made at the bottom was that it is not sterile. Long before humans descended, there was speculation that the deepest ocean might be lifeless, crushed by pressure and starved of energy. That assumption did not survive direct observation. Even at the greatest depths, life is present, sparse, slow-moving, and often small but undeniably alive. Organisms observed at the bottom tend to blend into their surroundings. Transparency is common, pigmentation is minimal or absent. Bodies are soft, sometimes gelatinous, sometimes fragile-looking, though that fragility is deceptive. These organisms are not weak. They are simply built for an environment where rigidity is a liability. Fish observed at these depths move deliberately, conserving energy. They do not dart or chase. Their muscles are adapted for efficiency rather than speed. Many lack gas-filled organs entirely, relying instead on tissue density to maintain position in the water. Their presence alone overturned long-standing assumptions about the limits of vertebrate life. Invertebrates are even more common. Amphipods, small shrimp-like scavengers, are frequently observed near the bottom. They move across sediment, feeding on whatever organic material they can find. Their abundance relative to other animals suggests that scavenging is one of the most viable survival strategies at extreme depth. When something falls from above, these organisms are among the first to arrive. Microbial life is perhaps the most important discovery of all, though it is the least visible. Sediment samples collected from the trench reveal thriving microbial communities. These microorganisms are not merely surviving, they are metabolically active, processing organic material, participating in chemical cycles, and shaping the environment in ways that are still being studied. Some of these microbes appear to rely on organic matter drifting down from the surface. Others use chemical energy derived from minerals in the sediment. Their presence confirms that life does not merely tolerate the deepest ocean, it integrates with it, forming ecosystems that function under conditions once thought prohibitive. Another unexpected finding was the presence of human-made materials. Even at the very bottom, traces of human activity have been detected. Microplastics have been found embedded in sediment. Chemical pollutants, transported through the ocean over long periods, have reached depths that were once assumed isolated. This discovery carries a quiet weight. It means there is no part of the ocean truly beyond the reach of surface activity. These materials do not appear as dramatic debris fields. They are small, often microscopic, fragments mixed into the sediment. Their significance lies not in their visibility, but in what they represent. The deep ocean was once imagined as a final refuge from human influence. The presence of pollution at its deepest point complicates that narrative. Another finding that surprised many researchers was the apparent calmness of the environment. Popular imagination often portrays the deep ocean as turbulent or chaotic. In reality, the bottom of the trench is remarkably still. Currents are weak. Sediment settles slowly. Movement is minimal. This stillness is not emptiness. It is stability. That stability allows for long-term processes to unfold without interruption. Sediment layers accumulate. Microbial communities persist. Chemical gradients remain intact. The bottom is not shaped by constant disturbance, but by rare events separated by long intervals of quiet. Among those rare events are geological disturbances. Evidence of past landslides and seismic activity can be seen in sediment structures. These events reshape portions of the seafloor abruptly, redistributing material and altering habitats. They are reminders that the trench exists at a tectonic boundary, and that deep calm does not mean geological inactivity. Chemical measurements taken at the bottom reveal a world with its own internal dynamics. Oxygen levels are low, but sufficient for life adapted to them. Nutrient concentrations vary subtly across small distances. The sediment-water interface hosts a complex exchange of chemicals, driven by microbial activity and slow diffusion. The environment is not chemically uniform. It is finely structured. Another important discovery concerns sound. At the very bottom, ambient noise levels are lower than in many other parts of the ocean. Surface noise attenuates with depth, and the trench's geometry can shield it further. This creates an acoustic environment that is unusually quiet, punctuated only by distant low-frequency sounds. This quiet may be essential for organisms that rely on subtle vibrations to detect food or threats. When lights are turned on during exploration, reactions are often muted. Some organisms retreat slowly, others remain motionless. There is little evidence of panic or rapid escape. This suggests that many deep-sea organisms are not accustomed to sudden stimuli. The environment does not reward quick reactions. It rewards conservation and stability. One of the more humbling aspects of visiting the bottom is how ordinary it appears once initial expectations fade. There is no sense of triumph, no dramatic revelation. The bottom does not feel like the end of something. It feels like another part of a system, operating under constraints different from those at the surface, but no less coherent. This ordinariness is deceptive. It is easy to mistake it for simplicity. In reality, the bottom hosts interactions that are subtle and slow but complex. Energy moves through the system in small increments. Matter is recycled efficiently. Life persists at the edge of what seems possible, not through excess, but through balance. Another important finding concerns the resilience of life at depth, Experiments and observations suggest that deep-sea organisms can be sensitive to disturbance. Physical disruption of sediment can take years to recover. Chemical changes can alter microbial communities for long periods. The system is stable, but not robust in the face of rapid change. This has implications for future exploration and potential exploitation. The bottom of the ocean is not empty space waiting to be used. It is an environment with its own dynamics, vulnerabilities, and limits. What we have found there suggests caution rather than opportunity. The discoveries made at the bottom also challenge the way we think about exploration itself. In many historical narratives, exploration is about discovery followed by utilization. The deep ocean resists that sequence. What has been found is not easily exploited. It does not invite development. It invites understanding. There is also a shift in scale that occurs when considering these findings. Individual organisms are small, changes are slow, impacts accumulate over long periods. This requires a different mindset, one that values patience and long-term observation over immediate results. Perhaps the most profound thing found at the very bottom is perspective. Standing or hovering at the deepest known point on Earth forces a reconsideration of what depth means. It is not a void, it is not a boundary, it is part of a continuum that extends from the surface to the planet's interior. The bottom is not silent, but it is quiet, not empty but sparse, not hostile but demanding. It exists without regard for human presence, and that indifference is instructive. It reminds us that the planet operates on scales, and according to rules that do not centre human experience. What we have found there does not resolve the mystery of the deep. It deepens it. Each observation raises new questions. How do these ecosystems respond to long-term change? How resilient are they to disturbance? How interconnected are they with surface processes we barely understand? The very bottom offers no conclusions. It offers evidence. It offers context. It offers a reminder that reaching a place does not mean understanding it fully. Presence is not comprehension. As exploration continues, the focus shifts again, from what exists there now to how that environment is changing, slowly but persistently, under forces both natural and human-driven. The trench is not frozen in time. It is part of a planet in motion, responding to pressures that extend far beyond its depth. For a long time, the deepest parts of the ocean were imagined as places beyond consequence, too far down, too isolated, too extreme to be touched by what happened at the surface. This belief was comforting. It suggested that no matter how altered the upper layers of the planet became, there would always be regions untouched, preserved by depth alone. The discovery of pollution at the deepest known point on Earth quietly dismantled that assumption. Pollution does not arrive at the bottom of the ocean dramatically. There are no clouds of waste, no obvious dumping grounds, no visual markers that announce human presence in the way cities or oil slicks do at the surface. Instead, it arrives slowly, fragment by fragment, molecule by molecule, carried by processes that are patient and indifferent. The deep ocean does not repel pollution, it collects it. Most pollutants that reach extreme depths do not sink directly. They travel indirectly, moving through food webs, attaching to particles, dissolving into water, and drifting downward over long periods of time. The journey from surface to trench can take years, sometimes decades. By the time pollutants arrive, they are often transformed, broken down, or redistributed, but they are still there. One of the most striking findings from deep-sea exploration has been the presence of microplastics in sediment collected from the deepest parts of the ocean, including the Mariana Trench. These are not large pieces of debris, they are tiny fragments, fibres and particles, often invisible without magnification. Their small size is precisely what allows them to travel so far. Plastics introduced at the surface enter the ocean through rivers, coastal runoff, and direct discharge. Over time, sunlight, wave action, and physical stress break larger items into smaller pieces. These fragments become suspended in the water column, where they can be ingested by organisms or attached to organic matter. As that organic matter sinks, it carries plastics with it. This process turns pollution into part of the marine snow that feeds the deep ocean. What falls from above is no longer just organic debris. It is a mixture of biological material and human-made fragments, drifting together through darkness. When it reaches the seafloor, it becomes part of the sediment, embedded in layers that will persist for centuries or longer. Chemical pollutants follow similar paths. Persistent organic pollutants, heavy metals, and industrial compounds enter the ocean from a variety of sources. Some dissolve in water, others bind particles. Many are resistant to degradation. Over time, they spread through ocean currents and sink into deeper layers. The trench, far from being isolated, becomes a terminal point in this slow redistribution. The presence of these substances at extreme depth is not immediately catastrophic in a visible way. There are no mass die-offs observed, no sudden collapses of deep-sea ecosystems attributed directly to pollution. This has led some to underestimate the significance of these findings. But absence of immediate drama does not mean absence of impact. Deep-sea ecosystems operate on slow timescales. Organisms grow slowly. Reproduction is infrequent. Recovery from disturbance can take decades or longer. This means that subtle changes, small increases in toxin levels or physical disruption, can have outsized effects over time. The system does not absorb shock well. It absorbs change quietly. Microplastics, for example, may not poison organisms outright, but they can interfere with feeding, digestion, and energy balance. When ingested, they occupy space without providing nutrition. They can carry chemical additives or absorbed pollutants into tissues. For organisms that already operate on minimal energy budgets, this inefficiency matters. Chemical pollutants can alter microbial communities in sediment, affecting the processes that recycle nutrients and organic matter. These microbial processes form the foundation of deep-sea ecosystems. Small shifts in their composition or activity can ripple upward, affecting larger organisms indirectly. The deep ocean is not a place of redundancy. There are few alternative pathways when one is disrupted. Another aspect that makes pollution at depth especially concerning is irreversibility. At the surface, pollutants can sometimes be diluted, degraded, or removed. Sunlight breaks down certain compounds, waves disperse others. Cleanup efforts, while limited, are at least conceivable. In the deep ocean, none of these options exist. There is no practical way to remove pollution once it has settled thousands of meters below the surface. This means that the deep ocean becomes a long-term archive of human activity. Sediment layers record what falls from above, preserving a chemical and material history of the surface world. Future scientists, if they exist, will be able to trace human influence not only through ice cores and tree rings, but through deep-sea mud. This archival role changes how we should think about the trench. It is not just a remote environment, it is a sink. A place where the byproducts of global activity eventually accumulate. The idea that pollution spreads evenly across the planet is misleading. It concentrates. It moves toward places where removal is impossible. There is a certain irony in this. The deepest parts of the ocean were once considered among the most pristine environments on Earth. Their inaccessibility was assumed to be protection. Instead, it has made them vulnerable in a different way. They receive pollution without receiving attention. Human awareness of deep-sea pollution lagged behind its arrival. For years, the focus remained on visible impacts at the surface, floating debris, contaminated coastlines, affected fisheries. These are immediate, tangible problems. Pollution at depth, invisible and inaccessible, did not provoke the same response. Only when direct samples confirmed the presence of human-made materials at extreme depth did the narrative shift. Even then, the implications were easy to downplay. The deep ocean is out of sight. The organisms affected are unfamiliar. The timescales involved stretch beyond political and economic cycles. Yet from a planetary perspective, the presence of pollution at the bottom of the ocean is a signal. It indicates that no part of the Earth system is truly isolated. Processes connect surface and depth in ways that are slow but persistent. Actions taken in one place propagate elsewhere, regardless of intent. This interconnectedness challenges the idea that environmental responsibility can be localized. Pollution does not stay where it is produced. It moves, it transforms, it settles in places that will never benefit from the activity that created it. The trench does not gain convenience, comfort, or wealth from human industry. It only receives its residue. The impact of pollution on deep-sea life is still being studied, and uncertainty remains. But uncertainty should not be mistaken for safety. The absence of clear thresholds does not mean thresholds do not exist. It means they are difficult to identify in environments where observation is limited and change is slow. There is also the question of cumulative effects. A single microplastic fragment may do little. A single chemical compound may be tolerated. But accumulation over time, combined with other stressors, could alter ecosystems in ways that are difficult to reverse. The deep ocean has limited capacity to adapt quickly. Evolution operates on long timescales. Human activity does not. Noise pollution, discussed earlier, also plays a role here. While not a physical contaminant in the traditional sense, sound alters deep-sea environments. Persistent low-frequency noise from shipping and industrial activity reaches great depths. Over time, this changes the acoustic landscape that organisms rely on for orientation and detection. Pollution is not only material, it is sensory. Climate change adds another layer. Changes in surface temperature, circulation patterns, and productivity influence how much organic material sinks to depth and how fast it arrives. This alters food availability for deep-sea ecosystems. Warming surface waters can reduce oxygen levels in deeper layers, affecting chemical balances. These changes interact with existing pollution in complex ways. The trench, once thought static and isolated, is revealed as part of a dynamic system responding to global change. Pollution is one expression of that change, but not the only one. What makes pollution distinctive is that it is unambiguously human in origin. It carries no ambiguity about cause. This raises ethical questions that do not have simple answers. If human activity affects even the deepest parts of the ocean, what responsibility do we have toward environments we will never inhabit? Does responsibility require direct interaction, or is connection enough? The trench cannot advocate for itself. Its inhabitants cannot be consulted. Decisions are made far away, often without considering their downstream effects. Some argue that because the deep ocean is resilient and changes slowly, it can absorb pollution without significant harm. Others point out that resilience does not imply invulnerability. A system can persist for a long time and still be fundamentally altered. Stability can mask degradation until thresholds are crossed. There is also the issue of precedent. Accepting pollution at the deepest point as inevitable risks normalizing it. It frames contamination as an unavoidable byproduct of progress rather than a choice shaped by policy, technology, and behavior. The fact that pollution reaches the trench does not mean it must. Technological solutions to pollution often focus on surface mitigation, reducing plastic production, improving waste management, limiting emissions. These measures, while essential, take time to show results. The deep ocean will continue to receive the legacy of past actions long after surface conditions improve. This time lag complicates accountability. Those who experience the consequences are not those who caused them. Future generations will inherit deep-sea environments altered by choices made decades earlier. The trench, silent and remote, becomes part of that inheritance. Understanding pollution at the end of the world requires adjusting expectations. There will be no dramatic moment of collapse, no clear line marking before and after. Instead, there will be gradual shifts, subtle changes in chemistry, slow accumulation of material that does not belong. From a scientific perspective, this makes monitoring essential but difficult. Baseline data is limited. Changes are hard to detect against natural variability. Long-term observation is required, yet funding and attention are often short-term. The deep ocean challenges not just technology, but institutional patience. There is also a risk of complacency. Because the deep ocean is far from daily life, its degradation does not provoke immediate response. Out of sight remains out of mind. But the presence of pollution at the deepest point undermines the idea that distance equates to separation. In a broader sense, pollution in the trench is not about the trench itself. It is about boundaries. It shows that boundaries we imagine between surface and depth, between human and non-human worlds, are porous. Actions do not stop where attention stops. The end of the world, if defined as the deepest point on Earth, turns out not to be an end at all. It is a receiving point, a place where consequences arrive quietly and remain. As understanding of this reality grows, the narrative of the trench shifts again. From a place defined by depth and extremity to a place that reflects the reach of human influence. It becomes a mirror rather than an escape. This reflection does not offer easy conclusions. It raises questions about how we define responsibility across distance and time. It suggests that preserving what remains untouched requires action, far from the places we wish to protect. And as we look beyond pollution itself, another realization emerges. The trench is not just passively receiving change, it is still changing on its own terms, shaped by geological forces that operate independently of human activity. These forces continue to reshape the environment slowly, reminding us that the planet's deepest places are not frozen backdrops, but active participants in Earth's ongoing transformation. It's tempting to think of the deepest parts of the ocean as finished places. Once you reach the lowest point, once the numbers stop increasing, once the descent finally ends, it feels natural to imagine that nothing more is happening. A final shape, a settled form. The idea of the trench as a static scar etched into the planet long ago and left unchanged is comforting in its simplicity. It is also wrong. The trench is still changing, not in ways that are easy to notice, and not on timescales that align with human attention, but continuously, relentlessly, and with no regard for observation. The deepest part of the ocean is not a fossil of past motion. It is an active boundary where the Earth is still rearranging itself. To understand this, it helps to step back from the ocean for a moment and think about what the trench actually is. It is not carved by water in the way a canyon is carved by a river. It exists because of plate tectonics, because enormous slabs of the Earth's crust are moving relative to one another. In the case of the Mariana Trench, one tectonic plate is sliding beneath another in a process known as subduction. This process does not happen smoothly. Plates do not glide like ice on ice. They grind, stick, flex, and release. Friction builds, stress accumulates. Eventually, that stress is released in the form of earthquakes. These earthquakes are not surface phenomena alone. Many originate deep below the seafloor, reshaping the trench from within. Each seismic event alters the geometry of the trench slightly. Slopes adjust. Sediment shifts. Sections of the seafloor may rise or sink by small amounts. Individually, these changes are minor. Collectively, over thousands or millions of years, they redefine the trench's shape. The deepest point today is not guaranteed to be the deepest point tomorrow in geological terms. Sediment plays a central role in this ongoing change. The trench acts as a natural funnel, directing material downward from surrounding slopes. Gravity pulls fine particles toward the deepest regions, where they settle and accumulate. This process never stops. Even when no dramatic events occur, sediment continues to rain down slowly, layer by layer. These layers do not simply pile up passively. Under extreme pressure, they compact. Water trapped between particles is squeezed out. Chemical reactions occur. Organic material decomposes. Over time, sediment becomes denser and more cohesive. The seafloor is constantly thickening, even as tectonic forces may be pulling it downward. This creates a quiet tension. Subduction drags material into the earth. Sedimentation adds material on top. The trench is shaped by both loss and gain, sinking and filling simultaneously. Which process dominates depends on location, time, and geological conditions. The balance is not fixed. Occasionally this balance is disrupted abruptly. Earthquakes can trigger submarine landslides, sending massive volumes of sediment cascading down trench walls. These events can reshape large areas in moments, burying existing surfaces and creating new ones. In such cases, the seafloor you might have visited one year could be unrecognizable the next, not because of erosion by water, but because of gravity acting on unstable slopes. These landslides do not announce themselves loudly at the surface. They may generate tsunamis in rare cases, but often they go unnoticed except by instruments. Their effects are recorded in sediment layers, where chaotic deposits interrupt otherwise orderly accumulation. The trench carries its own memory of these events, written in mud rather than stone. Volcanic activity also contributes to change, though less directly. In regions near subduction zones, magma generated deep within the earth can eventually find pathways to the surface, sometimes forming underwater volcanoes. Ash from distant eruptions can drift down and settle in the trench, adding new material. These inputs alter sediment composition and chemistry, influencing microbial activity and long-term geochemical processes. Chemical change is another quieter form of motion. Fluids circulate through the Earth's crust beneath the trench, carrying dissolved minerals and gases. Some of these fluids seep upward into the sediment, altering its chemical environment. These changes affect microbial communities, which in turn influence how organic matter is processed and how elements are stored or released. This means the trench is not chemically static. Oxygen levels, nutrient availability, and redox conditions vary over time and space. These variations may be subtle, but they shape what kinds of life can persist and how ecosystems function. Even without visible motion, the environment is dynamic. Temperature, while remarkably stable compared to surface waters, is not entirely constant either. Small variations occur due to fluid movement, geological activity, and long-term changes in ocean circulation. These changes are slow and slight, but in an environment where organisms are finely tuned to narrow ranges, they matter. One of the more difficult aspects of studying change in the trench is the lack of continuous observation. Most data comes from brief visits or instruments deployed for limited periods. These snapshots make it hard to distinguish between normal variability and long-term trends. The trench changes, but it does so on schedules that resist documentation. There is also the influence of surface-driven change, which arrives indirectly. Shifts in ocean circulation affect how much organic material sinks to depth. Climate-driven changes in surface productivity alter food supply for deep ecosystems. These effects are delayed and dampened, but they accumulate. The trench feels surface change as a faint echo rather than a direct experience. Over long timescales, these surface influences can alter sedimentation rates and chemical inputs. A period of increased productivity at the surface might leave a subtle signature in deep sediment layers. A long-term decline might reduce energy availability, affecting deep-sea communities gradually. The idea that the trench is still changing also applies to its role in the broader Earth system. Material subducted at trenches does not disappear. It is recycled into the mantle, contributing to volcanic activity elsewhere. Water carried down with sediment influences mantle chemistry. The trench is a gateway in a planetary circulation system that operates over millions of years. From this perspective, the trench is not an endpoint. It is a transition zone between surface processes and deep earth dynamics. What enters it eventually re-emerges in altered form. The deepest point on Earth is part of a loop, not a terminus. For humans, this challenges the notion of finality. We like to label extremes as fixed reference points: tallest, deepest, coldest. But these labels are temporary. They apply only within the current configuration of the planet. The Earth does not organise itself around records. It organises itself around physics. There is also a subtle psychological effect in recognising that the trench is still changing. It undermines the idea that there is anywhere completely removed from time. Even in a place without day or night, without seasons, without warmth, time still operates. Not as a cycle, but as accumulation and release. Change in the trench does not feel urgent. There are no countdowns, no visible thresholds, but it is continuous. The seafloor you imagine today is already slightly different from the seafloor of 1,000 years ago, and it will be different again 1,000 years from now. This continuity has implications for how we think about human influence. Pollution, noise, and climate-driven changes are being layered onto a system that is already in motion. They do not act on a static backdrop. They interact with ongoing geological and chemical processes, sometimes amplifying, sometimes dampening their effects. Understanding whether the trench is still changing is therefore not a question with a simple yes or no answer. It is changing in some ways and not in others. Its overall position remains, its existence as a trench persists. But its details, its contours, its chemistry, its biology are in flux. This flux is slow enough to feel like stillness, especially to surface observers. But stillness is a matter of scale. What looks motionless at one scale can be active at another. The trench operates on a scale where patience is required to notice change. For scientists, this presents a challenge. How do you study change in a place where access is rare and signals are faint? How do you distinguish natural variation from long-term trends? These questions are still being worked through, with no easy solutions. For the rest of us, the idea that the deepest part of the planet is still evolving offers a different kind of insight. It reminds us that extremes are not static monuments. They are processes. They exist because forces are acting, not because forces have finished. The trench, then, is not a frozen endpoint at the bottom of the ocean. It is an active margin shaped by pressure, gravity, chemistry, and time. Its depth is a momentary measurement within a much longer story. As attention shifts again, another perspective emerges. Beyond geology and change, the trench also occupies a peculiar place in human understanding. It marks not just a physical extreme, but a boundary of what we know and how we know it. The question becomes less about how the trench is changing, and more about what it represents in the landscape of human knowledge. There are boundaries that exist in the physical world, and then there are boundaries that exist in the mind. The trench occupies both at once. It is a measurable place, defined by depth and coordinates, but it also marks a line where certainty begins to thin. Beyond that line, knowledge does not stop, but it changes character. It becomes slower, more conditional, more dependent on inference rather than experience. The trench is not just the deepest place on Earth. It is one of the clearest examples of where human knowledge transitions from familiarity to approximation. Most of what humans know about the world comes from repeated contact. We learn places by being in them, returning to them, observing how they change from day to day and season to season. Cities are understood because people live in them. Forests are understood because people walk through them. Even remote deserts and polar regions, though harsh, are accessible enough to allow prolonged study. The deepest parts of the ocean do not allow this kind of relationship. The trench resists routine presence. It cannot be visited casually. It cannot be monitored continuously with human senses. Every piece of information about it arrives mediated through instruments, machines, and indirect measurements. This does not make that information invalid, but it does shape its limits. knowledge of the trench is fragmented by necessity. When people talk about the bottom of the ocean, they often speak with confidence. Numbers are cited, maps are shown. Diagrams give the impression of clarity. But beneath that clarity lies a patchwork of data points collected at different times, using different methods under different conditions. Large gaps remain between those points, filled in by models and assumptions. This is not unique to ocean science, but the trench makes it especially visible. The deeper you go, the harder it becomes to confirm what you think you know. Measurements can be precise without being complete. Observations can be accurate without being representative. A camera image shows exactly what was in front of the lens at that moment, and almost nothing beyond it. This creates a peculiar situation where the trench is both well-defined and poorly understood at the same time. Its existence is not in doubt. Its general shape is mapped. Its approximate depth is agreed upon. And yet, its detailed structure, its variability, and its long-term behaviour remain only partially known. One reason the trench marks a boundary of knowledge is that it challenges the human reliance on vision. For most of history, seeing was knowing. Observation meant looking directly at something. In the trench, vision is artificial and constrained. Light must be brought in. Cameras must interpret darkness. What is seen is filtered through lenses, sensors, and processing algorithms. Sound replaces sight as a primary source of information, but sound introduces its own ambiguities. Acoustic data must be translated into spatial representations. Echoes must be interpreted. Assumptions about sound speed and reflection must be applied. The result is knowledge that is robust but indirect. We know the trench largely through how it responds to signals we send into it. This reliance on indirect methods means that uncertainty is always present. Small errors in assumptions can lead to larger uncertainties at extreme depth. A slight variation in sound speed, a minor drift in navigation systems, a brief equipment malfunction can alter results. These uncertainties are managed carefully, but they cannot be eliminated. The trench also sits at the boundary of what technology can currently tolerate. Instruments pushed to these depths operate near their design limits. Pressure, corrosion, and isolation all increase the risk of failure. Each mission represents a balance between ambition and caution. As a result, exploration proceeds slowly. Data accumulates incrementally rather than comprehensively. This slow pace contrasts sharply with how quickly information accumulates in more accessible environments. Satellites can monitor entire continents daily. Sensors can record atmospheric conditions continuously. The deep ocean does not offer that scale of coverage. Each data point is expensive, difficult, and rare. As a result, scientific understanding of the trench relies heavily on extrapolation. Patterns observed in one location are cautiously applied to others. Processes inferred from laboratory experiments are assumed to operate similarly at depth. These assumptions are reasonable, but they remain assumptions until tested directly. This is where the trench becomes a philosophical boundary as well as a scientific one. It forces an acknowledgement that knowledge has gradients. Some things are known directly, some are known indirectly, some are suspected but unconfirmed. The trench exists in the space where those categories overlap. It also challenges the idea that more data always leads to certainty. Even as technology improves, some aspects of the trench may remain resistant to full understanding, not because they are unknowable in principle, but because the cost and difficulty of observation impose practical limits. Knowledge is constrained not just by curiosity but by feasibility. The trench highlights a difference between knowing that something exists and knowing what it means. We know the trench exists. We know it is deep. We know life exists there. But understanding how that life functions over long time scales, how ecosystems respond to change, and how geological processes interact with biology remains incomplete. This incompleteness is not a failure, It is a reminder that the planet is larger and more complex than any single method of inquiry can capture. The trench becomes a reference point for humility. It shows that even on our own planet, there are environments where certainty remains provisional. There is also a cultural dimension to this boundary. Human stories about exploration often emphasize conquest and mastery. The trench does not fit comfortably into that narrative. It has not been conquered. It has been visited briefly. It has been measured imperfectly. It has been observed in fragments. It remains largely indifferent to those efforts. This indifference reshapes the meaning of exploration. In the context of the trench, exploration is not about ownership or dominance. It is about contact and retreat, about learning what can be learned and accepting what cannot, at least for now. The trench also exposes a gap between public perception and scientific reality. Popular representations often suggest that the deepest parts of the ocean are fully known, neatly mapped, and well understood. In truth, large portions remain unmapped at high resolution. Biological surveys are sparse. Long-term monitoring is rare. This gap matters because it influences how people think about risk, responsibility, and preservation. It is easier to assume that something is understood and managed than to accept that it remains largely unknown. The trench resists that assumption. It remains a reminder that ignorance still exists even in an age of data. At the same time, the trench does not represent ignorance in a simple sense. It represents a frontier where knowledge advances differently. Instead of rapid discovery, progress comes through careful accumulation. Instead of certainty, understanding is probabilistic. Instead of control, there is accommodation. This mode of knowing is uncomfortable for societies accustomed to speed and resolution. It requires patience. It requires tolerance for ambiguity. It requires accepting that some questions may remain open for long periods. The trench also acts as a boundary between disciplines. Understanding it fully requires geology, biology, chemistry, physics, and engineering. No single field can explain it in isolation. This interdisciplinary demand complicates research but also enriches it. Each perspective adds depth, but none provides a complete picture. This complexity reinforces the idea that the trench is not just a place, but a convergence. It is where different processes intersect and where different kinds of knowledge must interact. The difficulty of integrating these perspectives contributes to the sense that the trench lies at the edge of comprehension. There is also an emotional boundary at work. For many, the trench evokes discomfort. Not fear in a dramatic sense, but unease. It is a place where familiar anchors are missing. No light, no landmarks, no easy exit. This emotional response can influence how knowledge is pursued and interpreted. Avoidance plays a role here. Humans tend to focus on environments where engagement feels manageable. The trench does not invite engagement. It demands preparation, resources, and acceptance of risk. This naturally limits attention and investment. Yet despite these barriers, the trench continues to draw interest. Precisely because it sits at the boundary of knowledge, it serves as a test of how far understanding can extend. Each new observation, however small, pushes that boundary slightly outward. The trench also reframes what it means to know a place. Knowing the trench does not mean having complete information. It means having enough understanding to ask better questions. It means recognizing patterns without assuming completeness. It means being aware of uncertainty rather than pretending it does not exist. In this way, the trench functions as a corrective to overconfidence. It reminds us that knowledge is always partial, always situated within limits imposed by tools, perspectives, and environments. The deepest place on Earth remains one of the clearest demonstrations of that truth. As exploration continues, the boundary shifts gradually. Better instruments, longer deployments, improved models all extend understanding. But the boundary does not disappear. It moves. This movement is important. It shows that boundaries of knowledge are not walls. They are gradients. The trench lies deep within that gradient, marking a region where certainty fades but curiosity remains active. And as attention moves beyond knowledge itself, another question begins to surface. What does a place like this, existing at the edge of what we can know, reflect back at us about how we think, how we explore, and how we define our place on the planet? Standing at the edge of the ocean usually means something physical. Feet near water, a horizon stretching outward, the sense of open space balanced by solid ground beneath you. But there is another kind of edge that does not require proximity or movement. It exists entirely in thought. Standing mentally at the ocean's edge means confronting a place you will likely never reach, yet knowing with certainty that it is there. The trench occupies this mental shoreline more clearly than almost any other place on Earth. You do not need to see the ocean to imagine its depth. Once the idea is introduced, it settles into the mind with surprising weight. Miles of water stacked vertically, pressure increasing steadily, light thinning and then vanishing. A bottom that is not really a bottom. These facts taken together create a sense of distance that is not horizontal but inward. It is not about how far away something is, but how inaccessible it feels. This inaccessibility changes how the mind relates to the place. Most environments we think about are navigable in principle. Mountains can be climbed, forests can be walked through. Even space, abstract and hostile as it is, feels conceptually reachable through technology. The deepest ocean resists this framing. It is reachable only briefly, only indirectly, and only through layers of protection. For most people, it remains permanently imagined rather than experienced. Standing mentally at the ocean's edge involves recognizing that limitation and sitting with it rather than trying to overcome it. It is an unusual posture in a culture accustomed to progress and access. We're used to believing that if something exists, it can eventually be reached, mapped, and understood fully. The trench quietly disagrees. When people first learn about the depth of the ocean, the reaction is often disbelief. The number feels exaggerated. 11 kilometers does not align easily with everyday experience, but once accepted, that number begins to distort perspective. Mountains feel smaller, buildings feel temporary, human structures feel thin, the mind recalibrates scale. This recalibration does not happen all at once. It unfolds gradually as the imagination traces the descent layer by layer. Surface waters, twilight zones, darkness, pressure, stillness. By the time the bottom is reached mentally, the surface world feels distant, almost hypothetical. Standing at this edge is not about fear, it is about perspective shift. There is a peculiar calm that can accompany this shift. Unlike edges associated with danger or risk, the mental edge of the deep ocean does not demand action. You cannot fall into it accidentally. You cannot misstep. The separation is absolute. That distance creates space for reflection rather than urgency. This may explain why the deep ocean often appears in contemplative contexts rather than adventurous ones. It invites thought more than movement. It encourages questions rather than plans. What exists where the ocean ends downward? How does life adapt to conditions so different from our own? What does that say about the flexibility of existence itself? These questions do not require answers to be meaningful. They function as anchors for thought, points around which reflection can organize itself. Standing mentally at the ocean's edge is less about learning new facts, and more about letting known facts rearrange how the world feels. The trench becomes a reference point for limits, not just physical limits, but perceptual ones. There are places that challenge not only our ability to go there, but our ability to imagine being there. The mind reaches a point where it must stop adding detail and accept abstraction. That acceptance can be uncomfortable, but it can also be clarifying. In everyday life, abstraction often feels like a loss. We prefer detail, specificity, familiarity. The trench reverses that preference. The absence of detail becomes part of its significance. Not knowing exactly what every square meter looks like does not diminish its reality. it reinforces it. Standing mentally at this edge also invites comparison. The deep ocean sits beneath us, hidden and ignored most of the time. Above us is the sky, visible and expansive. We talk often about looking up. We talk less about looking down, yet the downward distance to the trench rivals the upward distance to low Earth orbit. Both represent extremes. One captures imagination more readily than the other. This asymmetry reveals something about human psychology. We are drawn to openness and light. We are cautious around enclosure and darkness. The deep ocean combines darkness with enclosure in a way that resists romanticization. It does not offer vistas. It does not offer spectacle. It offers compression and absence. And yet the trench is not empty. Knowing that life exists there complicates the emotional response. Darkness is no longer synonymous with void. Pressure is no longer purely destructive. The environment supports existence in forms adapted to its constraints. This realization shifts the tone from unease to curiosity. Standing at the mental edge becomes an exercise in humility. It highlights how narrow human comfort zones are compared to the range of conditions life can tolerate. It also highlights how much of the planet operates independently of human awareness. The trench does not wait to be understood. It does not respond to observation. It simply persists. There is also a temporal dimension to this mental stance. Thinking about the trench often brings long timescales into focus. Sediment accumulating over thousands of years, plates moving over millions, microbial processes unfolding slowly in stable darkness. These scales dwarf human lifespans and reshape how urgency is perceived. Standing at the edge, the present moment feels less dominant. The mind stretches backward and forward, considering continuity rather than immediacy. Problems that feel overwhelming at the surface can feel smaller when placed against geological time. This is not a dismissal of those problems, but a reframing of their scale. The trench also challenges assumptions about boundaries. We often imagine boundaries as lines that separate. Land from sea, surface from depth, known from unknown. The trench blurs these distinctions. It is connected to the surface through sediment, sound, and chemical exchange. It is connected to the Earth's interior through subduction. It is not isolated. It is integrated. Standing mentally at this edge means recognizing connection where separation was assumed. The surface world influences the deep, and the deep participates in planetary cycles that eventually influence the surface. The boundary is conceptual rather than absolute. This realization carries ethical weight. If the deepest parts of the ocean are connected to surface activity, then distance does not absolve responsibility. Actions taken far away propagate downward. The trench becomes part of the same system we inhabit, even if we never see it. There is also a personal dimension to this mental edge. Thinking about the trench often triggers introspection. Limits prompt reflection. What are the limits of individual experience, of understanding, of control? The deep ocean does not offer answers, but it frames the questions differently. In a world saturated with information, places that remain largely unknown acquire symbolic importance. They remind us that knowledge has edges, that certainty is contextual, that mystery is not a failure state but a natural condition. Standing mentally at the trench is an encounter with that condition. This encounter can be unsettling, but it can also be grounding. It shifts attention away from constant accumulation and toward presence. You cannot scroll your way to the bottom of the ocean. You cannot summarize it fully. You can only hold its existence in mind and let it influence perspective. The trench also resists personalization. It does not care who you are, what you believe, or what you value. It offers no validation. This neutrality can be refreshing in a world where attention is often directed back toward the self. At the mental edge of the ocean, the self becomes small, not in a diminishing way, but in a contextual one. There is relief in that smallness. Not everything depends on us. Not everything is for us. Some things exist entirely outside our concerns. The trench is one of them. Standing mentally at the ocean's edge is not about imagining yourself there physically. It is about acknowledging a place that redefines scale, patience, and limitation. It is about recognizing that the planet contains environments that will never align with human needs, and that this misalignment is not a problem to be solved. The trench becomes a counterpoint to surface narratives of expansion and mastery. It suggests another mode of relationship with the world, one based on observation without occupation, curiosity without conquest. It asks what it means to know without possessing. This mode of relationship is rare in modern life. Most interactions with environments involve modification, building, extracting, reshaping. The trench resists this by default. Its conditions make modification impractical. Inaccessibility becomes protection, not through intention, but through physics. That protection is not absolute, as pollution demonstrates, but it does create distance. Standing mentally at the edge involves recognizing both the fragility and resilience of that distance. The trench is protected from direct intrusion, but not from indirect influence. This duality adds complexity to the mental image. The trench is not a sanctuary in the idealized sense. It is not untouched. It is affected. But it is affected slowly, quietly, without spectacle. That quietness demands a different kind of attention. When thinking about the trench, there is a temptation to search for meaning, to assign symbolism, the deepest point, the end of the world, the final boundary. These labels are understandable, but they risk oversimplifying. The trench does not exist to symbolize anything. It exists because of tectonics, gravity, and time. And yet symbolism emerges anyway, not because the trench intends it, but because humans project it. Standing mentally at the edge is as much about observing that projection as it is about observing the place itself. It reveals how humans respond to extremes, to limits, to environments that resist assimilation. This response often includes a mix of awe, discomfort, curiosity, and restraint. The trench does not invite emotional extremes. It does not provoke fear in the way predators do. It does not inspire wonder in the way bright ecosystems do. Its impact is quieter, more introspective. That introspection can linger. Once the idea of the trench settles into the mind, it becomes a reference point that surfaces unexpectedly. When thinking about scale, when considering limits, when reflecting on what lies beneath everyday experience, it remains present not as an image, but as a concept. Standing mentally at the ocean's edge does not require resolution. There is nothing to conclude. The trench does not demand understanding to justify its existence. It does not wait for interpretation. It simply remains. As thought drifts away from this edge, something else comes into focus. The trench does not only reflect the planet's structure, it reflects aspects of human nature. Curiosity, restraint, projection, humility. It acts as a mirror, not by showing us ourselves, but by showing us what exists beyond us. That reflection leads naturally to a broader question. If a place like this can exist, operating entirely outside human rhythms and priorities, what does that suggest about how we see ourselves in relation to the planet? Not as observers standing apart, but as participants within a much larger system whose deepest parts continue, quietly, regardless of attention. When humans look into the deepest parts of the ocean, it can feel like the gaze is one-sided. We observe, measure, speculate. The trench appears passive in this exchange, a silent subject of study. But reflection does not require intention. Sometimes it happens simply because something exists outside our usual frame of reference. The deep ocean reflects aspects of us not because it responds, but because it refuses to adapt to our expectations. One of the first things it reflects is how strongly human understanding is shaped by comfort. Most of what we call knowledge comes from places where we can remain present for long periods of time. We learn environments by living in them, returning to them, modifying them, and building routines within them. The deep ocean denies all of that. It cannot be occupied. It cannot be made familiar. This forces us to confront how much of our confidence depends on proximity and control. When control is removed, the limits of our assumptions become visible. We often assume that environments hostile to us are hostile in general. The deep shows how narrow that perspective is. Conditions that would destroy a human body are neutral, even ordinary for other forms of life. This does not make humans fragile in a moral sense, but it does place our physiology in context. We're adapted to a thin layer of the planet, and that adaptation shapes our worldview more than we usually acknowledge. The deep also reflects our relationship with extremes. Humans have a long history of defining themselves through records: tallest, fastest, farthest, deepest. These labels create a sense of progress and mastery. The deepest part of the ocean resists that narrative. Reaching it once does not make it known. Measuring it does not make it mastered. The record exists, but it feels strangely hollow. This hollowness reveals something important. Extremes do not automatically grant meaning. Meaning comes from interaction, interpretation, and consequence. The trench allows interaction only briefly and at great cost. The consequence is knowledge, but knowledge that remains partial. The meaning then is not triumph, but perspective. Another reflection emerges in how we talk about danger. The deep ocean is often described as hostile, unforgiving, lethal. These descriptions are accurate in relation to human biology, but they also reveal how easily we equate unfamiliarity with threat. The trench is not aggressive. It does not act upon us. It simply exists under conditions that do not align with our needs. This distinction matters. It shifts the narrative from one of opposition to one of mismatch. The deep is not something to be conquered because it is not an adversary. It is an environment that operates independently of human concerns. Recognizing this challenges a long-standing habit of framing nature as something that either supports us or opposes us. The deep also reflects our discomfort with invisibility. Much of the ocean is out of sight, and what we cannot see tends to feel less real. Before deep-sea exploration, it was easy to imagine the depths as empty or monotonous. Direct observation disrupted that assumption, but only partially. Even now, much of the deep remains unseen, and that unseen status affects how seriously it is considered. This tendency extends beyond the ocean. Environmental issues that are visible provoke faster responses than those that are hidden. The deep ocean suffers from this bias. Pollution at depth feels abstract compared to pollution on beaches or coastlines. The trench reflects how perception influences responsibility. There is also a reflection in how we handle uncertainty. In many areas of life, uncertainty is treated as a problem to be solved quickly. In science, it is often framed as a gap to be closed. The trench forces a different posture. Some uncertainties persist not because of lack of effort, but because of inherent constraints. Access is limited. Observation is intermittent. Systems are complex. Accepting this kind of uncertainty requires patience and restraint. It requires resisting the urge to oversimplify or overstate conclusions. The deep reflects how comfortable we are, or are not, with incomplete understanding. It exposes the tension between curiosity and humility. Another aspect it reflects is how we assign value. Environments that support human activity are often valued more highly than those that do not. Fertile land, accessible resources, navigable waters receive attention and protection because they are useful. The trench offers no immediate utility. It does not support agriculture, settlement, or transport. Its value lies almost entirely in what it teaches us about the planet and about life. This kind of value is harder to defend in systems driven by short-term return. The deep ocean reflects how easily usefulness becomes a proxy for worth. When something cannot be used, it risks being ignored or dismissed. Yet the trench contains information critical to understanding Earth systems, from tectonics to carbon cycling to the limits of biology. The deep also reflects our tendency to anthropomorphize. When we describe the trench as mysterious, forbidding, or alien, we are projecting emotional qualities onto a physical environment. This projection can be helpful as a storytelling device, but it can also obscure reality. The trench is not mysterious in the sense of hiding secrets deliberately. It is simply difficult to observe. Recognizing this projection helps clarify our relationship with the unknown. The unknown is not inherently meaningful. It becomes meaningful when it intersects with our curiosity, fear, or values. The trench reflects how humans create narratives around absence as much as presence. There is also a reflection in how we think about resilience. The deep ocean is often described as resilient because it persists under extreme conditions, but resilience does not mean immunity. Life there is adapted, not invulnerable. Disturbances can have long-lasting effects because recovery is slow. This distinction mirrors a common misunderstanding in human systems. Endurance is often mistaken for robustness. A system can endure for a long time and still be sensitive to change. The trench reflects this nuance clearly. Its ecosystems are stable, but they are not flexible. They tolerate consistency, not disruption. The deep further reflects our assumptions about progress. Technological advancement has expanded access to many environments, leading to an implicit belief that all barriers can eventually be overcome. The trench challenges this belief. While technology enables brief access, it does not eliminate the fundamental constraints imposed by pressure, darkness, and distance. This does not mean progress stops. It means progress changes character. Instead of expanding presence, it refines observation. Instead of control, it emphasizes care. The deep reflects a model of engagement based on limits rather than expansion. There is also a reflection in how humans relate to time. Surface life is dominated by urgency. Deadlines, growth curves, rapid change. The deep operates on different timescales. Processes unfold slowly. Change accumulates gradually. This contrast can be disorienting, but it can also be instructive. Thinking about the trench often introduces a sense of long duration. Geological time, evolutionary time. These scales diminish the dominance of the immediate. They do not make present concerns irrelevant, but they place them within a broader context. The deep reflects how scale alters significance. Another subtle reflection concerns presence itself. Human experience is often defined by being somewhere, occupying space, leaving marks. The trench resists this mode of existence. Human presence there is temporary and leaves little trace beyond data and, unfortunately, pollution. There is no lasting footprint of habitation. This resistance challenges the assumption that presence equates to importance. The trench exists regardless of whether we visit it. Its processes continue without acknowledgement. This independence can feel unsettling, but it also offers relief. Not everything depends on human attention. The deep also reflects our relationship with silence. In everyday life, silence is often treated as absence or discomfort. In the deep, silence is a condition. It is not empty. It carries information through subtle vibrations and chemical signals. Learning to interpret that silence requires patience and different sensory priorities. This has parallels in human communication. Not all information arrives loudly. Some signals are slow, indirect, and easy to miss. The deep reflects the value of attentiveness over immediacy. There is also a reflection in how we respond to limits on imagination. Certain aspects of the trench resist visualization. Pressure cannot be felt second-hand. Darkness without light reference is difficult to imagine. The mind reaches a point where it must stop adding detail and accept abstraction. This acceptance reveals how imagination works. We rely on analogies drawn from experience. When experience fails, imagination falters. The deep reflects the boundary between what can be pictured and what can only be acknowledged. The trench also mirrors how humans define their place in the natural world. For much of history, nature was seen as something external, something to be tamed or used. More recently, there has been a shift towards seeing humans as part of natural systems. The deep reinforces this latter view. It shows that human systems operate within a planet that has layers of activity far beyond daily awareness. Recognizing this can influence how responsibility is understood. If the deep ocean is connected to surface processes, then surface actions carry deeper consequences. The trench reflects the reach of those actions, even when intention is absent. There is also a reflection in how rarity shapes value. Few humans have been to the deepest parts of the ocean. This rarity lends weight to those experiences and to the places themselves. But it also highlights how much of the planet remains functionally unvisited. The deep reflects the limits of exploration even in a technologically advanced society. This does not diminish exploration. It reframes it. Exploration becomes less about completion and more about sampling, less about claiming and more about learning. The trench reflects an ethic of restraint by necessity. Another aspect it reflects is curiosity itself. Human curiosity is often restless. It seeks closure. The deep offers curiosity without closure. Questions remain open. Observations raise new uncertainties. This sustained curiosity without resolution is uncomfortable, but it is also intellectually honest. The trench also reflects how humans respond to indifference. Many environments respond to human presence visibly. Plants grow where we cultivate them. Animals react to disturbance. The deep ocean's response is minimal. It does not acknowledge presence in any obvious way. This indifference can feel humbling. Humility is a recurring theme in what the deep reflects. Not humility as self-denial, but as recalibration. It adjusts the scale at which we place ourselves. It reminds us that intelligence, technology, and culture exist within a much larger framework that does not revolve around them. The deep also reflects our storytelling instincts. Faced with environments that resist familiarity, humans create narratives, monsters, abysses, final frontiers. These stories reveal more about human psychology than about the environments themselves. The trench quietly resists these narratives by being neither dramatic nor empty. What replaces drama is persistence. Life persists. Processes persist. Change persists. The trench reflects a version of existence that is not optimized for speed, efficiency, or spectacle. It is optimized for continuity. This continuity challenges surface-level assumptions about success and progress. Growth is not constant. Activity is not always visible. Stability is not stagnation. The deep reflects alternative modes of functioning that are valid within their context. In reflecting on the trench, humans also confront their own boundaries of attention. It is easy to forget places that do not intersect with daily life. The deep tests whether value depends on relevance. Does something matter only if it affects us directly, or can it matter because it exists? The trench offers no answer, but it frames the question clearly. It exists without permission, without invitation, without explanation. It reflects back whatever perspective is brought to it. For some, it reflects insignificance. For others, connection. For others still, responsibility. The deep does not dictate interpretation. It provides contrast. Perhaps the most honest reflection it offers is this: humans are capable of understanding far more than they can directly experience, but that understanding is always shaped by limits. The trench sits at one of those limits, marking the edge of what can be reached, sensed, and known. Standing in relation to that edge does not require resolution. It requires awareness. awareness that the planet contains dimensions that will always exceed human scale, awareness that knowledge expands without eliminating mystery, awareness that existence does not depend on recognition. As attention drifts beyond this reflection, there is a sense of movement back toward the surface, not as a retreat, but as a return. The deep remains where it is, unchanged by contemplation. What changes is perspective. And with that shift, the journey naturally turns toward closing the distance, not by descending further, but by carrying what has been reflected back into the shallower world where attention began. Drifting back toward the surface does not feel like reversing a journey. It feels more like loosening a grip. The pressure eases gradually. Darkness thins in stages. The environment does not transform suddenly, and neither does perspective. What has been encountered at depth does not stay behind. It follows quietly, carried upward as a shift in how familiar things are perceived. As ascent begins, the first noticeable change is not visual. It is mechanical. Instruments adjust, systems recalibrate. The numbers that once climbed relentlessly now move in the opposite direction. Pressure decreases, but not in a way that invites relief. It simply becomes less absolute. The deep does not release its hold all at once. It relaxes it slowly. Sound changes before light does. The acoustic environment grows busier. Distant noise filters in more clearly. The quiet that defined the deepest regions becomes layered, filled with faint signals from above. This gradual return of sound complexity is subtle, but it signals connection. The deeper world is no longer acoustically isolated. It is being reabsorbed into a broader system. Light returns even more slowly. There is no moment when darkness ends. Instead, it weakens. At first, there is only the faintest suggestion of illumination from above, not enough to see by, but enough to hint that direction still exists. This faint glow does not reveal objects, it reveals orientation. Up becomes meaningful again. As light strengthens, colour does not immediately follow. The world remains muted. Blues and greens appear first, subdued and incomplete. Contrast improves before detail does. The environment becomes legible in stages, like an image gradually coming into focus after being blurred for too long. This gradual return mirrors how understanding often works. Insights gained at depth do not arrive fully formed. They surface slowly, reshaped by context. What was abstract becomes relatable. What felt distant begins to connect with everyday experience. Ascending through the water column, layers that were previously passed without comment now feel distinct. The return of temperature variation, however slight, marks a change in how the body and instruments interact with the environment. Warmth, even minimal warmth, carries familiarity. It signals conditions that align more closely with surface life. Movement becomes more apparent. Currents are felt rather than inferred. Particles drift visibly. Life becomes more active. The stillness of the deep gives way to subtle motion that feels busy by comparison. The ocean transitions from a place of patience to a place of activity. This transition does not invalidate what exists below. It contextualizes it. The deep is not replaced by the surface. It is layered beneath it, supporting and interacting in ways that remain largely unseen. The ascent reveals continuity rather than separation. At some point, the idea of a bottom fades. Attention shifts from what lies beneath to what surrounds. The vertical dimension becomes less dominant. The ocean begins to feel wide again rather than tall. This shift is psychological as much as physical. Depth recedes as a primary reference, yet the awareness of depth remains. It does not disappear when light returns. Knowing that miles of water lie below changes how the surface is perceived. Waves feel thinner. The boundary between air and sea feels more fragile. The surface becomes less of a foundation and more of a threshold. Approaching shallower depths, familiar patterns re-emerge. Light scatters more freely. Colour returns more fully. The environment becomes visually rich. This richness can feel almost overwhelming after the restraint of the deep. The abundance of stimuli contrasts sharply with the minimalism below. This contrast highlights how accustomed humans are to environments saturated with information. The deep strips that saturation away, leaving only what is necessary. Returning to the surface reintroduces complexity, but with a lingering awareness of how much of it is optional rather than essential. As ascent continues, time begins to feel structured again. There are cues, changes in light suggest progression. Movement feels purposeful. The timeless quality of the deep dissolves, replaced by rhythms that align more closely with human perception. Time resumes its familiar role as organizer rather than background. Yet something subtle remains altered. The sense of urgency that dominates surface life does not immediately return. The deep leaves behind a residual patience. After encountering an environment where change unfolds slowly and persistence outweighs speed, surface timelines can feel compressed, almost rushed. This lingering effect is not dramatic. It does not announce itself. It shows up in small ways. A pause before reacting. A longer look at something familiar. A moment of recalibration when confronted with scale. The deep adjusts expectations quietly. As the ascent nears completion, there is no sense of closure. The surface is not a destination in the way the bottom was imagined to be. It is simply where attention started. Returning to it does not resolve questions raised at depth. It reframes them. The trench does not offer answers that can be carried back neatly. It offers perspective that resists simplification. The knowledge gained is not a list of facts, but an altered sense of proportion. What matters shifts slightly. What feels absolute becomes relative. Once back near the surface, the ocean resumes its familiar appearance. Light dances, waves move, reflections scatter. From here, nothing suggests the immense vertical world beneath. The surface does not advertise what it conceals. It never has. This concealment is part of what makes the ocean enduringly compelling. It holds depth without displaying it. It allows daily life to proceed without constant reminder of what lies below. This separation enables function, but it also enables forgetting. Drifting back toward the surface does not erase what was encountered. It integrates it. The deep becomes a reference point rather than a focus. It informs understanding without demanding attention. There is also a quiet recognition that the journey downward was always conceptual as much as physical. Few will ever descend into the deepest parts of the ocean. Most will encounter them through thought, through mediated images, through reflection. The ascent, then, is also conceptual. It is the process of carrying those reflections back into everyday awareness. This carrying does not require constant remembrance. The deep does not need to be kept in mind actively to exert influence. Its existence alone is enough. Knowing that such an environment exists beneath the surface changes how the surface is interpreted, even when the thought is not explicit. The ocean's depth becomes part of the background understanding of the world. Like gravity or geological time, it does not need to be contemplated constantly to matter. It shapes context simply by being real. As attention settles again into familiar surroundings, the contrast between surface and depth softens. They are no longer opposites. They are layers of the same system. What happens above affects what lies below. What occurs below participates in cycles that eventually influence the surface. This interconnectedness lingers as a quiet insight rather than a conclusion. There is no need to summarize or resolve it. The deep does not ask for interpretation. It exists independently of understanding. Drifting back toward the surface is not an ending. It is a repositioning. The deep remains where it is, unchanged by observation. What changes is orientation. Perspective broadens, scale adjusts, the ocean continues to move, light continues to scatter, life continues to adapt across layers that rarely meet. Somewhere far below, pressure remains constant, darkness remains complete, and persistence continues without notice. And somewhere closer to the surface, attention resumes its usual patterns, now informed by the awareness that beneath them lies a world that operates according to entirely different rules, patiently, continuously, without pause.